Hi everyone, welcome again. My name is Martin Yanev, a software engineer and a computer science professor at Fitchburg State University. And in this 3-hour tutorial, we're going to talk about the Security Enhanced Linux or SELinux. This video will help you to gain practical skills on how to implement and manage mandatory access control efficiently. I will help you to learn how to configure the SELinux policies, manage user roles, and troubleshoot very common issues. This course will consist of figures, presentation slides, as well as hands-on coding examples. If you like long tutorials like this one, where you can learn things in depth, you can also consider subscribing my channel because we're planning to upload a lot of those IT courses in 2025. Now, let's get started.
Security Enhanced Linux, commonly known as SELinux, brings a powerful set of additional security measures to your Linux system, significantly enhancing its capability to protect sensitive resources. To understand SELinux and its security model, let's dive into how this intriguing technology works and why it is essential for modern Linux environments. First, think of SELinux as the security guard in a high-security facility. While Linux incorporates traditional discretionary access control, DAC, which relies heavily on user permissions, SELinux layers on mandatory access control, MAC. This means that access controls in SELinux are not left at the discretion of users. Instead, administrators set policies that dictate what users and processes can do, regardless of their permissions under DAC. This layer of security is crucial in environments where sensitive data and critical operations are at stake. Imagine your Linux system is like a party where everyone has free access to the buffet, except for SELinux, which says, "Hold on a second, you can't just take what you please." It demands to know who you are and what you're allowed to take. Even if you're the party host, SELinux may have specific rules that prevent you from accessing certain dishes. Perhaps the chef wants to keep the secret sauce safe. This approach minimizes the risk of data breaches and unauthorized access, ensuring that your resources are only accessed by those who truly need them. Now, how does SELinux enforce these rules? Using policies, SELinux operates based on defined security policies that dictate the behavior of all system processes. Here, labels play a pivotal role. Every process and resource within the SELinux environment is labeled, and these labels determine what actions are permissible. Consider this. In the world of SELinux, every file, process, and user is tagged with a label that reflects its security context. When a process tries to access a specific resource, SELinux checks the associated labels against the defined policy. If the policy states that the requesting label cannot access the target label, bam, access is denied. This tagging system is how SELinux can maintain a stricter oversight of actions on the system, ensuring security remains intact. In this code snippet, we are defining a SELinux module specifically for the HTTP daemon, commonly known as HTTPD. The first line declares the module's name and version, HTTPD 1.0. This provides a clear identifier for the policy we are creating, which helps in managing and maintaining SELinux policies. Following this, the require block specifies the essential types and classes that will be used in our policy. Here, we indicate that we require the HTTPD T type, which represents our web server processes, and the HTTP port T type, designated for ports that HTTPD can use. The class TCP bind refers to the permission we want to define, in this case, the ability to bind to network ports. The final line of the code is the crux of the rule. It uses the allow statement to explicitly permit the HTTPD T type to bind to HTTP port T ports using the TCP bind action. This tight control ensures that the web server can only communicate through designated HTTP ports, thereby enhancing the security by minimizing the risk of unauthorized access or connections. Now let's look at this figure, which illustrates the fundamental components of SELinux policy enforcement. At the top, we see two key elements, the subject and the object. Each of these is represented as a circle labeled type. The subject is assigned properties that are crucial for understanding access control. Specifically, it has an associated name, SBJ_T, and attributes listed as attr1, attr2. This indicates the specific characteristics that define the subject's identity and capabilities within the SELinux policy framework. Now, moving to the right side of the figure, we find the object. Similar to the subject, it carries a name, objt, along with its own attribute, address3. These elements define the resource that the subject is attempting to access. The relationship between the subject and object is mediated by permissions, represented as a connection labeled access. This connection is crucial, as it shows that specific permissions, denoted as perm1, are required for the subject to interact with the object. Beneath these elements, we encounter the obj class, marked in blue and titled Object Class. This section encapsulates the permissions applicable to the object. The obj class is identified by the name obj class typical, presenting a structured approach to categorizing objects within SELinux. The access vector for this class is noted as perm1, perm2, indicating the array of permissions that can be granted for various actions the subject might want to perform on the object. Finally, the relationships depicted in the figure emphasize the hierarchical nature of access control in SELinux, where the subject's attributes and the object's permissions work in conjunction to enforce strict security measures. This ensures that every access request is thoroughly evaluated based on defined policies, reinforcing the system's integrity while managing complexity effectively. For instance, a system administrator may have broader access. Think of them as a VIP guest at our party, while an ordinary user might only have access to standard resources, the appetizers, not the secret sauce. This segregation helps minimize the impact if an account were to be compromised. An intruder would be limited in actions they could take. Why should you care about SELinux? Well, aside from its myriad security benefits, it provides peace of mind in a world where cyber threats are ever evolving. With SELinux in place, important resources are less likely to fall prey to vulnerabilities, which otherwise could lead to severe consequences, such as data leaks or system compromise. But wait, there's more. SELinux not only restricts actions based on policies, but also logs them for later analysis. This logging capability means that if something goes wrong, administrators can trace back what happened, aiding response and remediation efforts. Now let's look at Figure 1, which provides an overview of the mandatory access control system implemented through SELinux. At the center of the diagram is the SELinux framework, which serves as the backbone of the security architecture. Surrounding this framework are several components that work together to enforce security policies effectively. The System Security Policy Database is prominently displayed, serving as the repository for the various security rules and policies that SELinux enforces. This database feeds into the Access Vector Cache, AVC, which acts as a high-speed memory area for recently accessed permissions, allowing for quicker decision-making when applications request access to system resources. The AVC is crucial for optimizing performance while maintaining rigorous security standards. Moving along the workflow, we encounter the Policy Enforcement Server. This component is responsible for real-time enforcement of the policies defined in the security database. It ensures that all access requests are checked against the defined policies, thereby acting as a gatekeeper to system resources. Additionally, the SELinux abstraction and hook logic layer facilitates communication between the operating system's kernel and the various SELinux components, providing the necessary hooks for security decisions to be made quickly and accurately. The flow of events connects to Linux security modules, highlighting how SELinux integrates with the core Linux architecture. This integration allows SELinux to extend discretionary access control (DAC) mechanisms with mandatory access control, thus enhancing overall system security. The interactions are logged in the log file, which serves as an audit trail for security-related events, enabling administrators to monitor and respond to potential security incidents effectively. SELinux, therefore, comprises 5 basic components that collectively work to reinforce the security boundaries within a Linux environment. Understanding how these components interact is vital for system administrators aiming to leverage SELinux's full capabilities, ensuring robust protection against unauthorized access while maintaining system functionality. Enabling SELinux does not automatically start the enforcement of access control. You might think, hey, I just flipped the switch. But if SELinux can't find a policy, it pulls up its metaphorical chair and refuses to play until its rules are clear. It's like a strict teacher saying, no policy, no class. So before we dive into the nitty-gritty of SELinux and think we know how it operates, let's break down what that policy really is and how role-based access control, often referred to as RBAC, comes into play. Now let's look at the figure. This flowchart illustrates the process SELinux uses to manage system calls and access control based on its policy. It begins with a system call where SELinux first checks its status. If SELinux is disabled, the process will simply allow the access without any restrictions. On the other hand, if SELinux is enabled, the flow moves forward to log the access attempt in the audit log located at var/log/audit.log. Next, the figure indicates that SELinux checks its current mode. If the mode is set to permissive, the system allows the access, albeit while still recording the attempt for later review. However, if SELinux is operating in enforcing mode, the policy becomes more stringent. At this point, the figure highlights the necessity of consulting the security policy. If the requested access is permitted according to the policy, it is granted. Conversely, if the policy denies that access, the flowchart illustrates a termination of the request. This detailed sequence underscores the critical role that the SELinux policy plays in managing access control within the system. Without a well-defined policy, SELinux functions ineffectively, unable to enforce security or allow appropriate interactions. The figure succinctly encapsulates the layered approach to security, emphasizing how every action is checked against the established rules of the SELinux policy. Now, let's delve into role-based access control, or RBAC. This is where it gets interesting. In SELinux, roles are like VIP passes that determine who can access which areas of the system. They act as an intermediary between users and the actions they can perform. Imagine you're at a concert and different passes allow you to enter the general area, VIP sections, or backstage. Depending on which paths you hold, you gain different levels of access. This is exactly how RBAC operates. SELinux uses roles as the second part of what we call in a SELinux context, a four-part identifier that includes user, role, type or domain, and sensitivity level. Each part of that context plays an essential role in determining access controls. Simply put, SELinux roles dictate which processes can access which types of objects at any given moment. Now let's introduce some specific roles to give a clearer picture. On a typical SELinux-enabled system, you might find several predefined roles assigned to users. The first is the user R role, meant for everyday users. It's like the standard access badge. It allows users to engage with applications but limits interaction with critical system types. Then there's the sys-adm R role reserved for system administrators. Imagine holding the data superhero badge, capable of doing considerable deeds, but with some limitations where security is a concern. On the more privileged end, we have the ccadm RR role, enabling security administrators to change SELinux policies. It's a pivotal role that demands caution because the boundaries of system behavior can be altered. And let's not forget the unconfined R role. This is the Wild West of roles, providing a significant degree of freedom, but potentially exposing the system to risk if not managed correctly. So in this framework, while the system administrator manages the overall environment, the security administrator polices how that environment changes, ensuring safety while encouraging functionality. To explore the roles available in your SELinux-enabled system, you can use the command cinfo-role. This command provides a comprehensive overview of the roles defined in the SELinux policy currently in effect. Each role acts as a security boundary, controlling what actions the associated SELinux user can perform. When you execute this command in the terminal, it queries the relevant policy database and returns a list of all roles. This is particularly useful for understanding the permissions landscape of your system. By knowing which roles are available, you can make informed decisions about user access and privileges. Understanding these roles is essential for maintaining a secure environment, as they dictate the actions a user can undertake. With this information at your disposal, you can more effectively manage user access and ensure that only authorized actions are permissible, further reinforcing the security muscle of your SELinux setup. The code snippet provided represents a rule in SELinux that governs access control for processes. Specifically, it allows processes labeled with HTTPDT which typically corresponds to your web server, to bind to any TCP socket labeled with HTTP port T. This is achieved through the allow keyword, which is fundamental to policy rules as it explicitly grants permissions. The part of the code that specifies name bind indicates the type of action that is permitted, in this case, the ability to bind a network service to a TCP port. This permission is crucial for web servers, as they need to listen on specific ports to handle incoming web traffic. Without this rule, the SELinux policy engine would deny such actions, potentially preventing the web server from functioning correctly. Writing SELinux policies requires attention to detail to ensure that only the necessary permissions are granted, maintaining a secure environment. After crafting such rules, they need to be compiled into policy modules and integrated into a master policy file, which SELinux then enforces during operation. Now let's look at the figure. This diagram illustrates the complex interactions between various components involved in a security policy framework. At the top, we can see two pod security policies, labeled PSP-A and PSP-B, represented by the yellow and orange circles. These policies dictate security context for pods within the system, ensuring that only compliant workloads can be deployed, thereby bolstering overall system security. As we move down, we can observe the four rules, Rule A, Rule B, Rule C, and Rule D, highlighted in varying shades of gray. These rules define specific permissions and constraints under which security policies operate. The arrows leading from the security policies to the rules indicate that these policies grant permissions that are critical in shaping how roles and subjects interact with resources. Next, notice the roles depicted in blue: Role A, Role B, Role C, and Role D. Each of these roles encapsulates a set of permissions defined by the earlier rules. The diagram shows connections signifying that roles can be assigned to subjects, represented by the cyan circles: Subject A, Subject B, and Subject C. This assignment indicates which users or groups have specific access rights within designated namespaces, demonstrating the principle of role-based access control RBAC at play. The namespaces, shown in purple, delineate the scope of influence for each role, with the sum namespace and namespace B labels emphasizing resource segregation. This helps in managing access control more effectively across different operational contexts within the cluster, ensuring that security boundaries are maintained. Linking all these elements, the arrows indicate various relations, particularly how roles are connected to both security rules and subjects. This interconnectivity illustrates how policies are enforced and how specific entities are empowered to perform their tasks based on the permissions set forth by the overarching security framework. Finally, the annotations on the right provide additional context for configuration items, specifying types, verbs, and resources that tie back into the security and access management workflows depicted in the figure. This comprehensive view allows system administrators to fine-tune security settings while ensuring that the system remains resilient against unauthorized access. Once we enable SELinux on the system, it starts its access control functionality, as described in the previous chapter. Now, what exactly does that mean for us as administrators? Let's dive into the fascinating world of SELinux operations. Remember, SELinux is like having a vigilant guard at the gate of your system, ensuring that the right processes have access to the right resources. And like any good guard, it needs our guidance from time to time. Now let's look at this figure, which presents configuration information for SELinux on the system. The first section outlines the state SELinux can operate in. As indicated in the comments, SELinux can be set to one of three values: enforcing, permissive, or disabled. When set to disabled, SELinux does not operate and, in effect, does not enforce any policies. The next part of the figure addresses the permissive state. When SELinux is in this mode, it allows operations to proceed while logging any actions that would have been denied in enforcing mode. This serves as a warning mechanism, giving system administrators the insight needed to fine-tune policies without actually blocking access. In contrast, when SELinux is set to enforcing, it actively enforces security policies. This state is crucial for maintaining a secure environment, as it denies unauthorized actions and halts processes immediately, highlighting potential security violations. The figure also details the variable SELinux type, which can take on additional values. Currently, it's set to targeted, meaning only specific processes are protected under SELinux policies. There is also a mention of minimum, which refers to a modification of the targeted policy, providing a more limited scope of protection. Lastly, MLS indicates multi-level security protection, although it is not currently in use in this configuration. Overall, this figure encapsulates essential settings that govern how SELinux operates within the system, illustrating its flexibility and power in managing security. In the provided code, the command setenforce is used to manage SELinux modes on a Linux system. SELinux, or Security Enhanced Linux, operates in two primary modes, enforcing and permissive. To transition to permissive mode, where violations of SELinux policies are logged but not enforced, the command setenforce0 is executed. This can be useful for troubleshooting as it allows applications to run without immediate restrictions, making it easier to identify underlying issues. Conversely, restoring the system to enforcing mode is accomplished with the command setenforce1. In this mode, SELinux actively enforces its security policies, which helps protect the system from unauthorized access and other potential threats. While switching to permissive mode can seem like a quick fix for an application that isn't functioning correctly, it's vital to address the root causes of any errors rather than rely on temporary measures. Proper management of SELinux settings enables administrators to maintain a robust security posture while ensuring that applications operate smoothly. To check the current state of SELinux, you can use the command getenforce. This command quickly reveals whether SELinux is in enforcing, permissive, or disabled mode, providing a clear snapshot of its operational status. Understanding the state of SELinux is vital as it influences how access controls are enforced across the system. If you encounter a permission-denied error, it's essential to investigate the reasons behind it. This is where logging becomes critical. SELinux maintains detailed logs of denied access attempts, which can help administrators identify potential issues with current policies. To analyze the logs effectively, you can use the ausearch command. Specifically, running ausearch-m avc-recent-i will display all access vector cache AVC denials that have occurred recently. This command will help you pinpoint any permissions that may be causing conflicts, allowing for a better understanding of what adjustments might be necessary in SELinux policies to resolve the issues you're experiencing. This combination of commands, getenforce for state and ausearch for log analysis, is crucial for managing SELinux effectively. To adjust the access vector cache size in SELinux, you can modify the cache threshold by using the command echo 768/sysfs SELinux/avc/cache threshold. This command writes the value 768 to the file that controls the AVC cache size, effectively increasing the number of entries it can hold. The value you choose should be based on your system's workload. Raising it can help enhance performance, particularly in environments with frequent permission checks. After making this change, you can verify that the cache threshold has been updated by executing the command cat/sys/selinux/avc/cache threshold. This will display the current value set for the cache threshold, allowing you to confirm that your adjustments have been successfully applied. By tuning the access vector cache, you can achieve more efficient resource access management in your system, ultimately improving its responsiveness and throughput. To manage SELinux policies effectively, it's important to know how to work with SELinux booleans. The command getSebool-a is used to list all the available booleans on your system. This is crucial because it provides an overview of the toggles that you can manipulate to adjust SELinux's behavior without making significant code changes. By reviewing these booleans, you can identify which ones may be affecting your application or service. For instance, if you find that your web server, HTTPD, is being denied access to the network due to SELinux policies, you can resolve this by modifying the appropriate boolean. The command setSebool phttpdd can network connect on enables this specific boolean, allowing the HTTPD service to establish network connections. The -p flag ensures that the change is permanent, maintaining your security adjustments across reboots. This method of utilizing booleans allows you to fine-tune SELinux's security posture while still permitting essential functionalities to operate smoothly. The command seminage permissive a -t is used to modify the SELinux policy for a specific service, in this case, the minina service. By applying this command, you are designating the minina t domain to run in permissive mode. In permissive mode, SELinux does not enforce the security policies against the specified domain, allowing it to execute without restriction. This is particularly useful for troubleshooting purposes, as it enables you to observe the service's behavior without being hindered by potential denial problems that could arise from strict security policies. Using SELinux in this flexible manner not only aids in identifying and resolving issues with the mini-delna service, but also helps maintain the overall security of your system. Other services and domains will continue to operate under their defined policies, thus safeguarding the broader environment while you troubleshoot the specific service. The seminage command is a powerful tool in the SELinux management suite, allowing administrators to tailor security policies to suit the unique requirements of their applications while effectively managing risks. In summary, understanding SELinux operations means becoming familiar with how to navigate its three states, interpreting denial messages, utilizing the access vector cache, and efficiently adjusting policies. With SELinux configured properly, you'll gain an additional layer of security, controlling who has access to what within your system. Remember, a SELinux is like a traffic officer. It directs where each packet of data can go without causing a crash. Just as you'd never ignore road signs, don't dismiss SELinux warnings. Tuning it will unleash its full potential while keeping your system secure and functional. So gear up for your journey with SELinux. It's time to take control and fortify your Linux systems. Happy configuring. SELinux is a fundamental component of security in Linux. It serves as a powerful mechanism for enforcing access control policies through mandatory access control (MAC). But as any administrator will attest, with great power comes great responsibility, and sometimes a good measure of confusion. Today we'll focus on one of the crucial aspects of SELinux, logging and troubleshooting. Why is this important? Well, SELinux developers recognize that a security-oriented subsystem like this can only thrive if it has robust logging and debugging capabilities. So let's dive in and explore how we can utilize SELinux logging and troubleshooting effectively. First things first, every action taken by SELinux must be auditable. This is not just a good idea, it's a necessity. Imagine running a security protocol that never tells you what it's doing or why it is doing it. Not a great scenario, right? Every denial, that is, every action that SELinux prevents, will be logged. This logging allows administrators to understand what is happening under the hood and take the necessary actions, such as tuning SELinux behaviors or altering policies. But how exactly does this logging happen? By default, SELinux sends its messages to the Linux audit subsystem, but only if the kernel has auditing enabled. This is crucial because if the audit subsystem isn't configured, you might miss out on a lot of valuable data. The assigned audit daemon picks up these messages and logs them in the /var log audit/audit.log file. So, if you find yourself scratching your head over SELinux denials, your first stop should be this log file. Now let's look at the figure displayed on the screen. This graph illustrates the SELinux access vector cache (AVC) operations, segmented by year. The vertical axis represents the number of AVC operations, while the horizontal axis delineates the months from December of one year to December of the following. Observing the data points plotted throughout the year, the chart tracks various components associated with SELinux activity. You'll note indicators for lookups, hits, misses, allocations, reclaims, and frees. Each of these categories provides insight into the interaction between applications and SELinux, helping you identify performance trends or issues over time. As you examine the graph, the presence of available data points across this timeline may vary, possibly leading to periods where specific operations show significant changes. This variance can be crucial for understanding when SELinux may have had an impact on application behavior, especially if you're troubleshooting specific misconfigurations or access denials. The last update timestamp at the bottom provides further context, indicating that this data was last refreshed on January 3, 2025. You can use this graph to monitor SELinux performance metrics systematically assisting you in pinpointing potential areas of concern related to access vector denials as you proceed with your investigation. Jargons aside, what does this mean? It tells you which process, identified by its PID and command name, tried to access what file, sensitive file, and why it was denied. This information is akin to finding breadcrumbs that lead you straight to solving the mystery of your application's frustration. If you're looking for a way to navigate the overwhelming amount of information in these logs, you may want to consider using a specialized command known as ausearch. This command is invaluable for knowledgeable administrators, as it enables more flexible querying of audit logs. For instance, if your focus is on AVC denials associated with your application, you can run a specific command to retrieve that information. This retrieves AVC denial events from the last few minutes. Think of it as a filtering mechanism to handle the heaps of logs and focus only on the culprits responsible for your application's misbehavior. After detecting an SELinux denial, the subsequent step is to determine how to address it. It's possible that the denial is due to improper file contexts. As a best practice, you should ensure that both files and processes possess the appropriate contexts. To check a file's context, utilize the command lsZFileName and compare it with SELinux's expected context. If you find that the context is incorrect, it can be amended using the con command. For example, if you find that a web server is having trouble accessing specific files, you may need to assign the correct type to those files. Remember, the key is in ensuring that every file, process, and application interacts harmoniously within the world of SELinux. If you're struggling to identify the issue, there's no need to worry. The Troubleshoot daemon can come to your rescue. This useful tool monitors SELinux denials and offers valuable insights regarding them. When installed, it can provide immediate notifications about what went wrong, along with possible solutions. While some organizations may hesitate to adopt these advanced security measures because of their initial complexity, tools like SETroubleshoot can significantly reduce the learning curve. To further investigate the situation, you can examine denial messages with the help of SELirt, which provides recommendations based on the denials reported. For instance, if you discover that Nginx is experiencing difficulties binding to a port you can proceed with, this can guide you toward possible resolutions while ensuring you don't get lost in the intricacies of SELinux policies. It's important to keep performance factors in mind. SELinux employs a system known as the Access Vector Cache, AVC, to remember the outcomes of prior access attempts. This functions similarly to a quick reference guide, allowing SELinux to bypass redundant checks when processing requests. When an access request matches an entry in the cache, the response is immediate, thus enhancing overall performance. If you encounter any performance challenges, you might consider adjusting the size of the AVC or reviewing its statistics for insights. Can provide valuable insights. Now let's look at the figure. This illustration provides a clear overview of how SELinux operates in the context of managing access between processes and system resources. In the diagram, the left side depicts a process represented by an oval. This symbolizes any application or executable that requests access to a resource. The arrows indicate the flow of information and permissions. When a process seeks to interact with a resource, it communicates with the SELinux layer. Central to this figure is the SELinux module, which contains both SELinux Policies and the Access Vector Cache, AVC. The policies dictate the rules governing access, determining whether a given action is permissible based on defined security contexts. The AVC acts as a cache, storing recent access decisions to streamline future checks, reducing system overhead. As the arrows illustrate, the SELinux policies interact with the incoming requests from the process. If the policies permit the access request, the process moves toward the resource with a green arrow signifying access granted. Conversely, if a request violates the defined rules, a red arrow points back, indicating a denial of access. This figure effectively captures the essential mechanics of SELinux, showing how it acts as a gatekeeper, ensuring that only authorized processes are allowed interaction with system resources. Understanding these flow dynamics is crucial for effectively using SELinux logging and troubleshooting tools, easing the administration of security on your systems. When we log into an SELinux-enabled system, the first thing we receive is an SELinux context tailored for our session. This context isn't just a random selection of letters. It contains essential components, including the SELinux user, role, domain, and optionally, a sensitivity range. Now, you might be thinking, wow, that sounds fancy, but what's the big deal? Well, managing user logins in SELinux is about more than just throwing everyone into a virtual room without a keycard. It's about defining who gets to do what while maximizing security. So buckle up and let's take a dive. The command.idz is an essential tool in understanding your current SELinux context on a Linux system. When executed, it provides a comprehensive output detailing your user identity in relation to SELinux's security framework. The results reveal the SELinux user, role, type, and any associated sensitivity levels. For instance, you might see components like unconfined U, unconfined R, and unconfined T in your output. The prefix unconfined signifies that the user has a broad set of permissions, indicating a less restricted access level by default. This is crucial for users who need to perform various tasks without running into overly stringent limitations imposed by SELinux policies. Understanding this command's output is vital for administrators and users alike, as it directly influences how they interact with the system and the permissions granted for executing certain tasks. By recognizing your SELinux context, you can navigate potential security constraints while ensuring that you operate within the defined security policies of the system. To check the available roles in SELinux, you use the command cinfo-role. This command is essential for administrators and users who need to understand their security boundaries within the SELinux framework. By executing it, you receive a comprehensive list of all the roles assigned to users on the system, which helps in identifying which permissions each role encapsulates. Roles are central to SELinux's role-based access control system, enabling fine-grained management of user privileges. Each user account has an initial role determined during the login process, dictating what actions they can perform and what resources they can access. This command provides visibility into these roles, allowing users to navigate their capabilities effectively. Understanding these roles is vital for administrative tasks, as users may need to switch roles based on the task at hand. Thus, the cinfo-role command becomes a crucial part of managing user access and ensuring that security policies are upheld, while also empowering users with the necessary information to operate within their defined parameters safely. To assign a SELinux user to a Linux account, you can utilize the seminage command line tool. The first step is to associate the SELinux user staff U with the Linux user Lisa. This is accomplished by executing the command seminage login-s staff U Lisa. In this command, the -a flag stands for add, indicating that you are creating a new mapping, while the -s flag specifies the SELinux user to be assigned. By running this command, you effectively grant the user Lisa access under the SELinux label staff-core U, allowing her to operate with the associated permissions. However, it's crucial to monitor and verify these mappings to ensure they are correctly configured. To display the current user mappings, you can use the command seminage login-l. This command lists all SELinux user assignments alongside their corresponding Linux usernames. By regularly checking this mapping, you can maintain security and compliance with your system's policies, ensuring that each user has appropriate permissions and access levels. Managing logins involves more complexity than merely granting access. If you aim to enhance the user login experience for various services, you can achieve this through PAM configuration files. For example, you might want to modify the login mapping for the root user when accessing the system via SSH. To implement this adjustment, you need to create a file within the /elinux/target@ins directory. With this, we've just specified, hey, whenever root logs in via SSH, assign them the user U SELinux user. It's a way to ensure that specific services have their unique access configurations. When using the command new role-r sysadmr, you're initiating a transition to a different user role within a security context, specifically elevating your privileges to that of a system administrator. This command is particularly valuable in environments where users need to perform administrative functions without logging out of their existing session. Upon executing this command, you gain access to additional privileges associated with the sysadmr role, which can include managing databases, modifying application settings, and linking various systems together. It's essential to understand that role transitions can significantly impact what actions you can perform on the system. Therefore, after switching roles, you should always verify your current context by using the IDZ command. This command will display your current security context, ensuring that you are operating under the correct role. Overall, the new role command streamlines the experience of accessing elevated permissions, boosting your efficiency while maintaining security protocols. The line in the sudoers file reads, myuser_all type equals db_t role db_all. This configuration grants the user myuser the ability to execute commands as any user on the system, specified by the first all, while using a specific text defined by the security enforcement mechanisms in place. The type equals db_t and role db_r components dictate the type and role that myuser will assume when executing commands. Essentially, these parameters provide the necessary permissions to interact with resources that are classified under the db_t type, which typically relates to database administration tasks. By allowing myuser to access the db_r role, you ensure that they can perform specific actions within the context of database administration without exposing them to the full array of system-level commands. This configuration is akin to providing a backstage pass, enabling controlled access to sensitive operations while maintaining security. Consequently, users can execute their required commands seamlessly and effectively, adhering to the principle of least privilege. As we wrap things up, remember that managing user logins under SELinux isn't merely about letting folks in. It's about maintaining a secure, orderly environment where roles are enforced, commands are monitored, and users know their boundaries. Proper handling of SELinux contexts and roles ensures that your systems remain guarded against unauthorized access while providing necessary functionalities to authenticated users. So, the next time you log into an SELinux-enabled system, just picture it as stepping into a well-guarded fortress where everyone knows their role, and paths to the treasure of data are carefully navigated. With all the information about SELinux users and roles, we have not touched upon how exactly applications or services create and assign an SELinux context to a user. As mentioned earlier, this process is primarily handled through the use of Linux's PAM, or Pluggable Authentication modules, which is crucial for maintaining security and flexibility in authentication. So let's dive into how this works. When a user logs into a Linux system, whether via the command line, a graphical interface, or through network services like SSH, they are not just receiving access to the system. They're also being assigned an SELinux context that includes an SELinux user, a role, and other important characteristics that define what they can do and access. This transition happens in a series of steps. First, the login process invokes PAM, which has various modules that manage authentication, session management, and account management. The specific PAM module responsible for working with SELinux is pam/selinux.so. This module is responsible for ensuring that, upon logging in, the correct SELinux context is assigned to the user. In the provided PAM configuration snippet for session services, the first line, session required pam/selinux.so close, is crucial as it clears the existing SELinux context, preventing any outdated or incorrect context from being carried over. This ensures that the security policies associated with the user session are correctly applied. Next, session required pam loginuid.so enables PAM to record the login UID, which is essential for tracking the user sessions and enforcing policies related to user activity. Following this, session required pam/selinux.so open sets the SELinux context appropriate for the user based on predefined mappings, establishing the correct security environment for the session. The line session required pam namespace.so introduces namespace support, which allows for the isolation of application environments within a session. This is particularly useful in containerized or multi-tenant environments. The entry session optional pam keyinit.so force revoke revokes any existing credentials and initializes a new keyring for the session, enhancing security by ensuring sensitive information is protected. Finally, the directives session include password auth and session include post login pull in standard session handling configurations defined in other files, ensuring a consistent setup across different services. Together, these components create a robust framework for managing user sessions securely and efficiently. But hang on, there's more. Not only do we need PAM to assign contexts, but we also need to ensure that SELinux can appropriately restrict access depending on the system's operational mode. For instance, if an administrator puts the system into permissive mode, we wouldn't want just anyone to have free reign. This is where another PAM module, PAM-SEPermit, comes into play. When SELinux is in permissive mode, PAM-SEPermit checks defined user lists to prevent certain users from logging in under relaxed security conditions. By default, you might see entries defined in a configuration file like /etc/security-sepermit.conf, where it lists users or groups that should be blocked during permissive mode. This keeps malicious actors at bay, even when the system is in a less restrictive state. The main takeaway here is that PAM modules provide a flexible method of enhancing our security posture without reinventing the wheel for every application. In this configuration snippet, we define the rules for poly instantiation by specifying the remapping of the /tmp and var tmp directories. The first line indicates that the original tmp directory is remapped to a new location, /tmpmp /, under the security context labeled as level root. This means that when users interact with this tmp directory, they are actually accessing a private instance that ensures they won't see or interfere with the temporary files of other users. Similarly, the second line achieves the same remapping for the /var tmp directory, directing it to /tmpimp/tmpinst/ with the same security level designation. This structure effectively isolates user environments, maintaining privacy and security while allowing necessary access to these temporary storage spaces. Setting the appropriate permissions is crucial in this setup. By carefully configuring these mappings, administrators can provide users with their unique subdirectories, ensuring safe and private operations without compromising system integrity or exposing sensitive data to unauthorized access. This approach enhances overall security and user experience in multi-user environments. The line session required PAM namespace.so plays a crucial role in configuring the pluggable authentication module, PAM, for managing user sessions. By including this line in the PAM session configuration files, administrators can enable support for Linux namespaces, which effectively creates isolated user environments. This isolation is essential for maintaining a secure and compliant system, as it ensures that users interact with their personalized views of the file system without interfering with one another. The required qualifier indicates that this module must succeed for the session to proceed. If it fails, the user session will be denied. By utilizing PAM namespace.so, each user can have distinct paths and visibility rules tailored to their specific roles and permissions. Such granularity enhances security, as it allows for the enforcement of SELinux policies at a finer level. Consequently, system administrators can configure access rights and visibility on a per-user basis, ensuring that sensitive information remains protected while still allowing for usability based on individual needs. This balance of security and usability is paramount in multi-user environments. Managing SELinux roles efficiently is crucial for system administrators. The command new role sysadm_r is specifically designed to facilitate this process. When a user who has access to multiple SELinux roles is logged in, they may need to switch roles to perform different tasks that require varying levels of access. This command allows the user to assume the sysadm_r role without the need to log out or close their session. Upon executing this command, the user will be prompted to enter their password for authentication. Once verified, they will transition seamlessly into the sysadm_r role, which typically grants them elevated privileges necessary for system administration tasks. This capability minimizes interruptions in workflow, as users can swiftly move between roles as needed, fostering efficiency and enhancing security. By using the new role command effectively, administrators can streamline their operations while maintaining strict role-based access controls within the system. This approach not only enhances user experience, but also consolidates access management, ensuring that users have the appropriate permissions for their required tasks. In the provided line from the //sudoers file, we see a configuration that allows the user myuser to execute commands with elevated privileges. This entry is structured to grant myuser access to run commands as any user, with an emphasis on specifying the SELinux context through the type and role parameters. By setting typewol sysadmt, the code specifies the SELinux type that will be associated with the commands executed by myuser. This association is significant as it enforces the correct security context under which the commands will be processed. The role sysadmr portion of the line indicates that when myuser uses sudo, they will assume the sysadmr role. This mechanism allows administrators to limit access to specific roles while maintaining a broader user context. Overall, this configuration exemplifies the flexible use of sudo in conjunction with SELinux, enabling controlled privilege escalation. It highlights how system administrators can enforce security policies, ensuring users operate within defined roles and types to effectively manage system security while minimizing potential risks. SELinux, or Security Enhanced Linux, is an advanced access control mechanism that's crucial for enforcing security policies in Linux systems. One of its foundational concepts is that it is heavily reliant on contexts associated with resources and domains associated with processes. So today, let's take a closer look at these two important components, file contexts and process domains. Before we dip into the technicalities, let's set the stage. Now let's turn our attention to the figure. This diagram illustrates the decision-making process of SELinux, particularly focusing on file contexts and how they interact with processes. At the top right, you see the Linux Security Module subsystem, which plays a crucial role in forwarding decisions to SELinux. This subsystem ensures that security policies are enforced systematically. In the center of the figure, we identify a specific SELinux context labeled systemu systemr http s0s0. Each component of this context breaks down into categories. The SELinux user is systemu, the SELinux role is systemr, the SELinux type here is httpt, and the sensitivity is indicated by S0. This structured context is vital for defining what the HTTPD process can access. Moving to the left, we find an interaction where the HTTP type is attempting to write to a file. This action is directed towards an Nginx process, which is also defined by its own context. The flow indicates that when a T seeks to write, SELinux must validate this request based on the defined contexts. Further down, we see the destination of the write operation, represented by hpd sysrw content T. This type explicitly allows read and write access to certain files associated with DokuWiki. The context systemu object_r ht sysrdo content T s0 indicates the permissions tied to this file type. Finally, the last part of the diagram provides details about the file path used for DokuWiki wiki files, located at /s webs localhost htdoc/dokuwiki/data. It also notes the owner as httpd, the group owner as http, and the permissions set to 755. This comprehensive overview showcases how SELinux manages access and security between processes and files through a well-defined context system. The first command, symonaj fcontext-t httpd sys content t /web is used to add a new file context rule to SELinux. Here we are defining that all files located in the sarv web directory along with its subdirectories and files should be labeled with the type httpd sys content t. This specific context type indicates that the files are web content, allowing web servers like Nginx or Apache to access them without any permission issues. The pattern /srvsweb/sta ensures that the rule applies not just to the directory itself, but also to any files and subdirectories within it. Following this, the second command, restore-con-rv//web, is executed to apply the newly defined context to the existing files within the specified directory. The -r option indicates that the command should operate recursively through all files and subdirectories, while the -v option provides a verbose output, letting you see what changes are being made. By running this command, SELinux updates the context of all relevant files in /web, ensuring they are marked as appropriate for web access and eliminating any potential access issues for the web server. To check the SELinux context of a specific file or directory, you can use the ls command alongside the -z option. By executing ls/zid/wo of localhost htdocs docuwiki, you prompt the system to list the details of the specified path while also revealing the security context assigned to the files within that directory. The output of this command will display the SELinux context, which includes information such as the user, role, type, and level associated with the file. Understanding this context is crucial, especially when troubleshooting access issues for web servers. If your web server is unable to serve certain files, it might be due to an incorrect SELinux context that prevents access. By examining the context output from the command, you can quickly identify if the permissions are aligned with what is expected for your web operation. Any mismatches can often indicate where the issue lies, allowing you to rectify the context without extensive investigation. Thus, using this command serves as an effective diagnostic tool for SELinux-related access problems. Next, let's shift gears and discuss process domains. Just as files have contexts, processes operate within certain domains in SELinux. The domain is defined by the context under which a process is executed, determining what actions the process can perform and what resources it can access. Imagine a process trying to read a sensitive file. If it runs under the wrong domain, and by wrong, I mean one that doesn't have permission, the operation will be blocked, a bit like trying to enter a secure area without the right badge. The default domain for processes launched by a web server such as Nginx might be something like HTTPDT. When the web server forks to create worker processes, these new processes inherit the parent's HTTPDT domain. However, there might be scenarios where you'll want to change the domain. This is where transitions come into play. The command csearch-t httpd-exec-t is a powerful tool used in SELinux for examining type transitions associated with a specific SELinux type. In this case, the maxT option signifies that we are interested in type transitions, while the maxT argument specifies the type we want to investigate, which is httpd-exec-t. When you execute this command, SELinux will return a list of possible transitions that can occur when a process executing a file labeled with the httpd-exec-t context attempts to perform actions that may lead to a domain change. This output will essentially inform you about the potential security context shifts available under your current SELinux policy settings, helping ensure that your system's security model is both functional and restrictive as needed. Understanding these domain transitions is crucial for system administrators because it allows them to manage permissions meticulously, ensuring that applications have the necessary access to resources while still adhering to security principles. By utilizing csearch, administrators can gain insights into how different processes interact within the system, making it an invaluable resource for maintaining a secure operating environment. Now let's look at this figure, which illustrates the process of domain transitions within SELinux. At the top, we have two allowed types, systemr and httpdt, both categorized under the context of higher privilege domains. The figure visually represents how SELinux manages permissions and transitions between these types. Focusing on the left side, we see the inadrt domain. This domain typically runs initialization commands within the operating system. The arrow pointing towards httpdt signifies a transition. This transition occurs when a process in the inadrt domain executes a command that requires access to the httpt domain, typically for services related to web hosting. Next, the figure also highlights the httpd-exec-t domain, which represents executable files within the httpt context. The connection between httpdt and httpd-exec-t indicates that processes in the httpt domain can read and execute files designated for that domain. The arrow labeled entry point suggests that upon reaching this domain, the process is granted the permissions necessary to interact with web services. Overall, this diagram encapsulates the flow of transitions between different domains and how SELinux enforces these rules, ensuring that only processes with the right permissions can interact across different types. Consequently, any attempt to deviate outside these established paths without appropriate privileges will lead to failure, as emphasized in the original script. To query actual running processes and gain insights into their security contexts, you can utilize specific commands such as ps-ez-grep nginx. This command retrieves a list of all running processes along with their associated security contexts. By filtering with grep nginx, you focus specifically on the nginx process, providing details on its running status and the security attributes that apply. Once you have identified the nginx process, you can further investigate its security context by using cat proc pid @/current, replacing pid with the actual process identifier. This command displays the current security context for the specified process, revealing its SELinux attributes. For example, you might see an output like system_r httpdts0. This output indicates that the nginx process operates within the httpdt domain, which is critical for understanding its permissions and access rights. This transparency is essential during debugging, especially when diagnosing access issues. Should the nginx process attempt unauthorized access, knowing its security context aids in swiftly identifying and troubleshooting the problem. File contexts and process domains in SELinux create a robust framework for managing and securing your Linux environments. By carefully assigning contexts to files and controlling the domains of processes, system administrators can define precise and nuanced access controls. The beauty lies in the fact that this control minimizes risks while allowing flexibility. Just remember, the next time your web server can't access a file, it's not that the file is playing hard to get. It probably just has the wrong ID badge. By understanding these foundational concepts, you can effectively manage SELinux in your environment and maintain a secure system that doesn't impede legitimate access. That's it for today. Thank you for tuning in. If you found this information helpful, give this video a thumbs up and subscribe for more deep dives into the world of Linux security. Stay secure, and see you next time. Modifying SELinux contexts is a crucial aspect of managing security within a Linux environment. Today, we will dive deep into how we can query and modify SELinux contexts effectively, ensuring that our systems remain secure and efficient. Let's get started. We now know how to set SELinux contexts, both directly through tools such as SECon as well as through the RestoreCon application, which queries the SELinux context list to know what context a file should have. But how does this all work? Well, SELinux uses a labeling mechanism that assigns a context to every file and process in the system. This context is crucial because the security policy implemented by SELinux relies heavily on these labels to determine access controls. The first command utilizes -fcontext to add a new file context for the directory /sr of web. The -a option stands for add, and the -t option specifies the type of the context, in this case, httpdsys content t. This particular context type indicates that the files within this directory are intended to be served by a web server, providing necessary permissions for the web server to access these files securely. The expression //web/that denotes that this context should apply not only to the directory itself, but also to all files and subdirectories within it. Once the context has been defined, the next step is to apply it, which is where the second command, RestoreCon, comes in. The -r flag makes the command recursive, meaning it will traverse through all subdirectories and files under /sr web, while the -v flag provides verbose output, helping you see what changes are being made. Overall, this command ensures that the new context is correctly assigned to all relevant files in the specified directory, reinforcing the security and functionality of your web server. In this tutorial, we delve into the configuration of the RestoreCon daemon, specifically focusing on the paths that are monitored for context changes. The two paths listed here in //services at conf are critical files in a Linux system. The /etc/services file contains information about network services and their associated port numbers, while /resolve.conf is responsible for DNS resolution, indicating how the system should query DNS servers. By adding these paths to the RestoreCon configuration, any modifications made to these files will trigger RestoreCon to automatically reset their SELinux contexts to the specified ones. This is particularly useful in environments where these files might be altered frequently, ensuring that they maintain their proper security contexts without additional manual intervention. By employing RestoreCon, system administrators can effectively safeguard these crucial configurations, ensuring consistent security policies. Once configured, changes can occur seamlessly in the background, allowing users to focus on their primary tasks while knowing that security settings remain intact. To begin the process of full file system relabeling in a CentOS-based distribution, the first step involves creating a specific file within the root directory. This is accomplished by using the command touch/auto-relabel. This command essentially creates an empty file named .auto-relabel at the root level of the file system. The presence of this file signals to the SELinux system that a relabeling is required during the next system boot. It acts as a trigger for SELinux to address any inconsistencies in file contexts, ensuring that everything aligns with the policy specifications. Once the .auto-relabel file is in place, the next command to execute is reboot. This command will restart the system, initiating the relabeling process upon boot up. During this time, SELinux meticulously checks each file, adjusting its contexts as needed. Be aware that this relabeling can considerably extend boot time, as it resembles a comprehensive inventory check of your files. After the reboot, any discrepancies in SELinux labels will be resolved, and your system will operate with enhanced security, having the correct contexts applied to all relevant files. In the context of managing file contexts on a Gen 2 system, you can utilize specific tools designed to simplify the process. One of these tools is fixfiles, which allows you to restore file context for a particular application, such as nginx. The command fixfiles-r-nginx restore specifically identifies the files associated with the nginx package and resets their context to default. By doing this, you ensure that the security context of the files aligns with the system's expectations, which is crucial for maintaining proper file permissions and access control. Another useful tool is rlpkg, which serves a similar purpose but focuses on a more streamlined approach to resetting context for installed packages. Running the command rlpkg nginx will refresh the file contexts related to nginx, offering a straightforward way to maintain system integrity without requiring a system reboot or extensive manual intervention. Both commands aim to facilitate easier maintenance for users, allowing for effective file management while keeping the system secure and efficient. By incorporating these commands into your routine, you can maintain a cleaner and more reliable environment. To check the current SELinux context settings of a file or directory, you can use the command ls-z/sorv/web. This command lists the files and directories in the specified path, web, while also displaying their associated security contexts. The -z option is crucial as it instructs the ls command to show the SELinux context information alongside the usual file attributes. By examining the output, you can identify the security labels that dictate how the system enforces security policies on those files and directories. Keeping a close eye on these contexts is essential, as it allows you to anticipate potential security issues before they escalate. Regular monitoring can help ensure that file permissions and security settings align with your intended access controls, promoting a proactive approach to security management. As the saying goes, an ounce of prevention is worth a pound of cure, and this holds especially true in the realm of system security, where misconfigurations can lead to significant vulnerabilities. In conclusion, mastering SELinux context is an essential skill for any Linux administrator. With tools like chcon, restorecon, and seminage, you can ensure your file system is labeled correctly, maintaining high security. And remember to double-check your labels. A mislabeled file can lead to access issues that can range anywhere from pesky annoyances to potential security breaches. Now, go ahead and put your newfound skills to the test. Happy labeling. Understanding SELinux networking becomes essential, especially when security is a priority in modern computing environments. Today, we will dive into the captivating world of SELinux and its networking capabilities, particularly focusing on two implementations, NetLabel and labeled IPsec. These technologies play a critical role in how SELinux maintains security and communication across networks, so buckle up and let's embark on this journey. Now, let's look at the figure illustrating the architecture of labeled networking within SELinux. At the top of the figure, we see two distinct entities, Server A and Server B. Server A houses several components, including the process labeled as Process A. This process is linked to two key elements, a labeled networking port, designated as local IBEN port T, and an open subnet manager, OpenSM process. The labeled port connects to port 0, which is associated with node A, demonstrating how local networking configurations are essential for data management and security enforcement. The left side of the figure depicts the labels associated with the networking processes. The label SUM_label_T is applied to process A in server A, reinforcing the concept that each element in this network has a specific security label that governs its access permissions. This label management helps in maintaining a structured data flow, crucial for safeguarding sensitive information from unauthorized access. Moving across to server B, we find another process labeled as process B. It is similarly connected to two network ports, port 0 and port 1, which are linked to node B. Both servers leverage the InfiniBand subnet, illustrated at the bottom of the figure. The InfiniBand partitions, labeled as local IBP key T for partition X and partition Y, indicate the boundaries within which the data transfers occur. This architecture ensures that the data retains its confidentiality while traversing through the network. Overall, the figure encapsulates the essence of how SELinux employs security labels and separates networking elements to fortify security protocols. By managing how data flows between these networks, the architecture not only enhances security, but also allows for the rigorous enforcement of mandatory access controls across the system. Let's begin by discussing NetLabel, a labeling framework designed to apply security labels to network traffic. Think of it as a way to mark packets, similar to how one might label a box before shipping it. Within the NetLabel framework, there are two main methods: fallback labeling and SIPSO, Common Interoperability Specification for Passports and Official Documents. The fallback labeling method allows for the assignment of labels to traffic associated with network locations that do not utilize labeled networking. This feature enables the enforcement of security mechanisms on traffic that would otherwise function without sensitivity labels. It's akin to having an umbrella ready when the weather looks uncertain. While it may not be required all the time, it becomes invaluable when the storms arrive. For instance, one could implement a fallback label specifically for traffic coming from a designated address. What this command does is assign a specific security label to any traffic coming from IP address 192.168.100.1 on the ETH0 interface. This way, labeled networking is active for this source, allowing SELinux to use this context for access control decisions. Now let's take a look at the figure. This diagram illustrates the relationship between different components involved in the use of SIPSO within the NetLabel framework. At the top, we have the IPsec-T entity labeled as Pluto, representing the IPsec implementation, which serves as the main interface for managing security associations. To the left, you'll find the IPsec-SPT, depicted as the Security Policy Database, SPD. This component plays a critical role in determining how packets are handled based on their security policies. The dotted lines indicate associations, such as setContext, which allows modifications to be made in line with the current security context. Below, we see a representation of the Mozilla T entity, specifically linked to the Firefox application. This shows how an application can request a security association. The association labeled setContext communicates the need for a security association while also establishing a connection with the dynamic allocation of security associations. Adjacent to Mozilla T, we observe another component labeled HTTPDT, which corresponds to the Nginx web server. Between the two application entities, there are associations for sending and receiving data. For instance, the send-to association allows Mozilla T to communicate with its own security context, while the ref-from association does the reverse for the HTTPDT entity. This flow illustrates the interaction between applications and the security context provided by IPsec, emphasizing how the sensitivity of the data is identified without transmitting the entire context. Notably, all these elements are orchestrated in the kernel space, where the Linux IPsec transform subsystem XFRM manages the underlying processes. In this configuration, we define a connection named rem1 rem2, which establishes a secure tunnel between two specified hosts. The parameter left equals 192.168.100.4 indicates the local host's IP address, while right equals 192.168.5 specifies the remote host's IP address. The configuration is set to automatically start the connection with auto equals start, which means that the tunnel will initiate as soon as the LibResWan service starts. Authentication is managed through the parameter auth_by equals secret, indicating that a shared secret will be used to validate each connection. Importantly, labeled IPsec equals yes activates the labeled IPsec feature, which ensures that all communications are processed with security context labeling, enhancing confidentiality and integrity. Lastly, the policy label systemu object r ipsec spdt s0 designates the security label associated with the traffic, defining the security context required for managing the IPsec policies and ensuring that sensitive data is properly handled throughout the transmission process. Now, you might be wondering about the access controls when using labeled IPsec. Here's where it gets intriguing. Labeled IPsec introduces some additional controls through SELinux. It requires defined security policy databases, SPDs, to determine when a communication should follow an IP policy. Security associations, SSAs, are concerned with maintaining one-way channels between hosts, including the necessary security information. The access privileges are nuanced. Domains wanting to initiate a communication must possess specific privileges against the source context. When everything is in order, your communication channels become fortified with robust security checks, allowing only authorized traffic to flow freely while denying any malicious attempts to infiltrate. Now let's bring this all together. Both NetLabel and labeled IPsec allow networks to maintain context awareness, essentially giving a sense of identity to network traffic. They ensure that sensitive information is treated with extreme caution, allowing administrators to implement strict controls regardless of the environments in which their systems operate. The essence of SELinux networking is about laying down the law, while the rules of who, what, when, and how things should travel. Proper configuration equips us with tools to effectively manage sensitive data across various networks, ensuring compliance with security policies. So the next time you set up a Linux environment, remember that it's not just about functionality, it's also about security. With SELinux, you have powerful tools at your disposal. Embrace them, configure them well, and you'll create a fortress for your network communications. And that concludes our tutorial on SELinux networking, where the labels never lie and security is always in style. Thank you for tuning in, and don't forget to like and subscribe for more insightful tutorials. See you next time. In an IPsec setup, there are a few key concepts that we need to grasp fully, especially when we're working within an SELinux environment. The first concept is the Security Policy Database, SPD. Think of it like the rulebook of our communications. The SPD knows what communication needs special handling and when it should kick into action. That means it identifies when communication should be processed with an IP policy and under what circumstances it should leverage a security association. Now let's look at the figure. This diagram illustrates the concept of a security association, SA, and its integration within a network architecture featuring two distinct networks. On the left, we see Network 1, represented by a green box labeled Network 1, which includes a NetLabel peer type, indicating the security labeling mechanism in use. At the center of the figure is the Linux server or desktop, serving as the hub for security protocols. This section is clearly marked and shows its relationship to both networks through a designated network interface. The server hosts the HTTP component, demonstrating the application layer that facilitates HTTP transactions. Moving to the right, we find Network 2, also highlighted in green, and featuring a similar NetLabel peer type structure. This network communicates directly with the Linux server, forming a secure connection. Consider the dashed lines indicating the flow of data between the networks and the server, which emphasizes the directionality of these connections. Below the main components, the diagram outlines various roles and security tags. The Standards section details how the HTTPD service binds to the related TCP sockets, indicating which services are permitted to communicate over this secure channel. Meanwhile, the Seek Mark optional area provides insight into packet labeling, showcasing how security-aware packet handling occurs between components like the HTTP server and PostgreSQL. Overall, This figure encapsulates the critical components and interactions required to establish a secure environment for data transfer between hosts in different networks, underscoring the importance of proper security association management. Lastly, we have the Security Association Database, SAD, which keeps track of all individual SAs. Now here's where it gets a bit interesting. In a labeled IPsec setup, these associations are no longer just indexed by the good old source and target addresses. No, we're stepping up our game. They are also indexed by the source context. This means that if you're operating on a Linux system engaged in such a setup, you might have dozens of SAs identified for a single communication flow between two hosts, each represented with its own client domain. So how does labeled IPsec enhance the overall security landscape? Well, it introduces a range of additional access controls via SELinux. Each entry in the SPD is given a context, meaning domains that wish to obtain an SA need to have the poll match privilege against this SPD context. This is akin to having your VIP pass for backstage access at a concert, allowing you the ability to initiate important actions securely. In terms of modifying the SPD, only those authorized can make changes, controlling modifications through the set context privilege as well. Generally, this privilege is bestowed upon the IPsec tools that operate in the background, an excellent point to remember when diagnosing connection issues. Now, if we're crafting policies that dictate IPsec communications, the involved domains must have sent to privileges with their own association, while also obtaining re-fee from privileges for the associations of the peer domains. It's kind of like ensuring both parties in a conversation have the right to speak and listen, defining the boundaries of those interactions, and bolstering security policies with stronger assurances. One interesting aspect to note is that while labeled IPsec cannot dictate whether programs like Mozilla T can communicate with others like HTTP directly, it can control how incoming communication is managed, ensuring that authorization checks are in place before any interactions occur. This aspect is crucial in preventing unauthorized access while ensuring a streamlined operation that balances usability and security. Now let's look at the figure illustrating the setup of a simple IPsec tunnel using the Libvirt tool. In this diagram, we see two VPN routers, labeled Router A and Router B, positioned on either side of a cloud labeled Internet. This setup represents the core of the VPN tunnel that securely connects two different locations, specifically a branch office on the left and a head office on the right. The VPN tunnel line between the routers signifies the encrypted connection established over the Internet, ensuring secure data transfer between the two offices. On both sides of the diagram, we have clusters of laptops representing the devices at the branch and head offices. This visual clearly distinguishes the two locations, indicating that each office group can communicate securely through the established VPN tunnel. Each VPN router serves as the gateway for its respective office, managing connections and ensuring that data packets are routed securely between the branch and head offices. This configuration underscores the importance of VPNs in protecting organizational data while facilitating seamless communication across different geographical sites. Initially, you will establish a shared secret that links the two hosts. For example, if the hosts are referred to as RAM1 and RAM2, the configuration for the shared secret would appear in the following manner. This neat line will help you establish a connection by setting the groundwork for securing the data that travels through your VPN. The provided code defines the basic configuration for a VPN connection using IPsec. The first line, left equals 192.168.100.4, specifies the local endpoint of the VPN, indicating the IP address of the local machine that will initiate the connection. Conversely, right 192.168.100.5 indicates the remote endpoint, which is the IP address of the machine you want to connect to. The auto=start directive tells the VPN service to automatically establish the connection when the service starts. This is crucial for ensuring that the VPN is active without manual intervention. The setting auth_by_secret specifies the authentication method, indicating that a shared secret will be used for securing the connection. Additionally, there are two settings for IPsec that have been commented out. The line hack labeled IPsec equals yes suggests that there is an option to enable labeled IPsec, which adds a layer of security through labeling. Similarly, policies label equals system u object r ipsec spdt s0 is also commented out, indicating that policy labeling can be implemented for access control. Keeping these settings commented allows for a straightforward initial testing phase of the VPN connection before introducing more complexity. When you're satisfied that things are running smoothly, it's time to enable labeled IPsec. Just uncomment those lines we commented out earlier in your configuration. Restart the IPsec service one more time, and your connection should be fortified with the enhanced benefits of labeled IPsec. In conclusion, SELinux paired with labeled IPsec provides a robust means of safeguarding communications in a Linux environment. The dynamic interplay between the SPD, SAs, and SAD equips administrators with the tools necessary to impose strict control over who can communicate with whom across a network. So make sure to take the time to understand these components and apply the SELinux policies effectively in your networking strategies. Trust me, your future self, still sitting on that hypothetical beach sipping a cold drink, will thank you for it. Sure. Here's the requested video script breaking down the topic of SELinux automation with Ansible in a structured way with engaging explanations. As technology has evolved, you might have noticed a significant shift in how we manage our systems. With the rise of large distributed application platforms, cloud services, and the high adoption of virtualized infrastructure, system administrators are moving towards infrastructure as code frameworks. Think of this as writing code to manage your infrastructure rather than manually configuring everything. It's like having a magic wand for your IT setup. When we say infrastructure as code, we're talking about orchestration and configuration tools that treat system configurations like programming code. This means you can manage everything from server setups to application deployments in a systematic, repeatable manner. This leads us to the exciting world of Ansible and how we can use it to automate SELinux management. First off, what is Ansible? Ansible is an open-source automation tool that allows you to configure systems, deploy software, and orchestrate complex IT tasks, all with minimal fuss. What's great about Ansible is its simplicity. It doesn't require any agents to be installed on remote servers. It operates over SSH. You could say that Ansible is like a polite guest. It just shows up, does its job, and leaves no mess behind. Now, SELinux might sound daunting if you're just getting started. SELinux, or Security Enhanced Linux, is a security layer added to Linux. It introduces an additional set of rules and policies that determine how applications can access files and resources. Think of it like the strict school rules that you might have hated as a kid, but ultimately kept you safe. The first line of code, yum install EPEL release, is a command to install the extra packages for Enterprise Linux EPEL repository on a CentOS system. This repository contains additional software packages that aren't included in the base CentOS repositories. By installing EPEL release, you gain access to a wider range of packages, including Ansible itself. This step is essential as it prepares your system to tap into these extra resources, ensuring that you can easily install additional software tools that may be necessary for managing your servers. The second line, yum install Ansible, is the command that actually installs Ansible on your control machine. The yum package manager handles the installation process, retrieving Ansible and all its dependencies from the repositories configured on your CentOS system. Once this command is executed successfully, Ansible will be ready to use, enabling you to automate the management of SELinux and other configurations across multiple servers efficiently. With both these commands executed, your system will be equipped with the tools necessary for effective automation. In the provided playbook, we begin by targeting all hosts listed in our inventory. The first task demonstrates how to set SELinux to enforcing mode by using the built-in SELinux module. The playbook specifies that the SELinux policy should be targeted, which is a common setting where only specific processes are restricted. By setting the state to enforcing, we ensure that SELinux actively prevents unauthorized actions, thereby enhancing the security of our servers. The second task illustrates how to manage SELinux booleans, which are additional settings that can fine-tune the behavior of SELinux. Here, we focus on the boolean called httpd enable home_dirs, which when enabled, allows HTTP scripts to execute from user home directories. By setting its state to yes, we facilitate this capability, which can be vital for certain web applications that require this functionality. Once the playbook is configured, running the command Ansible playbook site.yml will apply these configurations across all specified machines, optimizing both security and functionality with minimal effort. The first task in the playbook focuses on uploading your custom SELinux policy file to the target machines. Using the copy module, the playbook specifies the source of the custom policy file named test.sil, which resides locally. The destination on the remote machines is set to us/share custom test.sil. Additionally, the file is assigned ownership to the root user and group, with permissions set to 0644, allowing read and write access for the owner while enabling read-only access for others. This task ensures that the necessary policy file is in place before any further action is taken. Following the upload, the second task loads the custom SELinux module into the SELinux environment. This is accomplished through the command module, which executes the cmodule command with the -i option to install the provided policy file. Importantly, this task includes a when condition that checks if the result of the previous upload task does not indicate failure. This error handling is a precautionary measure to ensure that the custom policy is only loaded if the upload is successful, thereby enhancing the reliability of the playbook. Now let's talk a bit about idempotency. This is a fancy word, but think of it simply. It means running something multiple times won't change the outcome beyond the initial application. This is crucial in automation tools like Ansible to avoid unnecessary changes. For example, when loading SELinux modules, if it's already loaded, Ansible won't try to load it again. As we wrap up our introduction to using Ansible for SELinux automation, remember that it's about making your life easier and more secure. From ensuring consistent policy application to deploying custom configurations across hundreds of machines with precision, Ansible empowers you to automate like never before. And if your playbooks cause a hiccup, fear not. You have the flexibility to put SELinux into permissive mode temporarily and fix issues without feeling the pressure of that automation tool overriding your manual tweaks right away. Now let's look at the figure. This diagram illustrates a workflow involving a customer, specifically a playbook developer, and an AAP, Automation Analytics Platform Controller. The process begins with the developer interacting with a source control management repository where project content is managed. The developer can edit the project, which facilitates the use of the Ansible sign command to generate a checksum manifest and sign it. Next, attention is drawn to the synchronization process within the AAP controller. This section highlights the project sync function, where the AAP controller pulls the latest content from the source control management system. It then verifies the signature of the project files and recalculates the checksums as part of the project directory verification process. This verification ensures that the content has not been tampered with and maintains data integrity. Following verification, two potential outcomes are presented. If the validation fails, the user in the AAP controller will receive a message indicating that they cannot launch the job template. Conversely, if the validation succeeds, the user will be able to launch the job template without any issues. This clear distinction emphasizes the critical role of verification in maintaining security and functionality within the automation workflow. In this video, we're diving deep into the advanced management of SELinux using popular automation tools, Puppet, Chef, and SaltStack. If you've ever dealt with SELinux, you know it can be complex and a little daunting, but worry not. Today we'll break it down step by step, just like making that intricate cake you think is too hard to bake. Let's start with what SELinux is and why we need to manage it. SELinux, or Security Enhanced Linux, is a powerful security module that provides a robust mechanism for enforcing the separation of information based on confidentiality and integrity requirements. That's a fancy way of saying it adds extra security layers to our Linux system. However, managing SELinux can sometimes feel like trying to solve a Rubik's Cube. Challenging, but totally doable. Now, why should we harness the power of automation tools like Puppet, Chef, and SaltStack? These tools help us manage configurations and deployments on multiple systems simultaneously, ensuring consistency and saving us from tapping away on every single machine. Imagine not having to manually apply your SELinux policies across every server. Well, that's exactly what we'll achieve today. In the provided Puppet configuration, we define a class named Packed SELinux, which is instrumental in managing SELinux policies on the system. The first declaration is a file resource that ensures the directory /us/share/SELinux custom exists. By specifying ensure each directory and setting the mode to 0755, we ensure that the directory has the appropriate permissions and is available for the SELinux custom modules. Following that, we declare another file resource, which points to the SELinux policy module test.sil. This resource ensures the file is present at the designated path /us/share SELinux custom test.sil. We define the owner and group as root, and importantly, we utilize the source attribute to specify where Puppet can retrieve the module file from, specifically from the module's repository. The require attribute plays a crucial role as it establishes a dependency on the previously declared directory resource. This guarantees that the directory is created before attempting to upload the SELinux module. Additionally, we specify cell type USRT to ensure that the appropriate SELinux context is applied to the uploaded file, thus maintaining the system's security and integrity. In this section of the chef configuration, we start by creating a directory for our SELinux custom policies. The directory resource specifies the path /share SELinux/custom, assigns the ownership to the root user and group, sets the permission mode to 755, and indicates that this directory should be created if it does not already exist. This is essential for organizing our custom SELinux configurations in a designated location. Next, we utilize the cookbook file resource to manage the transfer of our test.sil file into the newly created directory. Again, we set the ownership to root, the group to root, and define the same permission mode. This action ensures that our CIL policy file is properly placed in the custom directory before it can be used. Finally, the execute resource attempts to load our SELinux module using the command /spin share/SELinux customs test.sil. However, before executing the command, it checks whether the mod is already loaded by using not if uslr/bin gloriapqq testdoor. This conditional check prevents unnecessary loading of the module and ensures that the operation is resource efficient. In this SaltStack configuration, we define a state called load_test_sil, which is responsible for managing an SELinux module. The configuration utilizes the SELinux.module state, which provides a high-level way to handle the installation and loading of SELinux modules within a system. The first parameter under this state is nameTest, which specifies the name of the SELinux module we want to load. Next, we define the source parameter, pointing to the location of our SELinux module file, /us/share SELinux/custom/.sil. This path indicates where SaltStack should look for the module to be installed. The install true directive tells SaltStack to proceed with the installation of the module if it is not already present. Finally, the unless condition checks if the module named test is already loaded on the system using the command simodule-l grep-q test$. If the check fails, i.e., the module isn't loaded, the installation will occur, ensuring that the SELinux module is only installed when necessary, thereby optimizing resource use and maintaining system integrity. This approach exemplifies the efficient management capabilities of SaltStack in larger environments. For all these frameworks, understanding idempotency is crucial. Idempotency means that applying the same configuration multiple times will not change the system after the initial application. So if you run your Puppet, Chef, or SaltStack code multiple times, it won't keep loading your test.sil file if it's already present. It's a bit like hitting snooze on your alarm. You really just need that one buzz to get your day started. Let's wrap up by discussing the need to customize SELinux actions that your chosen framework might not support out of the box. Sometimes you might find that specific SELinux actions are missing. In those cases, you're not stuck. You can always create custom scripts or commands to handle these specific needs and integrate them into your configuration management tool. For example, if there's a unique SELinux context you need to apply that's not handled by your tool, you can write a custom command on the fly, and that's where the flexibility of these automation tools shines. Now let's look at this figure, which illustrates the timing statistics for managing SELinux. The graph presents a comparison between two methods, the regular SELinux management processes and the CIL, Common Intermediate Language, for specific commands. On the horizontal axis, we see the different SELinux commands being executed: SELinux Policy Targeted Install, semodule-drhcs, and semodule-erhcs. The vertical axis indicates the time taken to complete these operations, measured in seconds. The blue bars represent the duration of the regular methods, while the red bars indicate the time required when using CIL. Focusing on the first command, SELinux Policy Targeted Install, we observe that the regular method takes approximately 20 seconds, whereas the CIL method shows a significantly reduced duration. This trend continues with the semodule-drhcs command, where the standard approach again takes longer compared to its CIL counterpart. Finally, looking at the semodule-erhcs command, we see a consistent pattern. The regular execution time is noticeably longer than that of CIL. This figure effectively highlights the efficiency advantages of CIL in managing SELinux tasks, showcasing how it can save time and streamline processes in our security management efforts. Systemd is a core component of many Linux distributions. Since its birth in 2010, many distributions have gradually adopted Systemd as the core init system, responsible for handling services and boot-up operations. Today, we will delve into the fascinating integration between Systemd and SELinux, two critical components that enhance security and system management in Linux environments. First, let's break down what Systemd is. Systemd is not just an init system. It is a suite of tools that manage system processes. It provides a standardized way of handling services, replacing the older sysvinit system, which relied heavily on shell scripts. With Systemd, everything is configured through unit files, which have a structured format and allow for the explicit definition of dependencies and service behavior. This makes managing services much more efficient and flexible. Additionally, with the advent of Systemd, we gained features like parallel service startup, which significantly reduces boot time. Now onto SELinux. SELinux, or Security Enhanced Linux, is a powerful security architecture integrated into the kernel that provides a mechanism for enforcing the separation of information based on confidentiality and integrity requirements. It operates under the principle of least privilege, meaning that every process and user is granted the minimum level of access necessary to perform their tasks. SELinux adds an additional layer of security by enforcing mandatory access controls, which limit how processes interact with each other and with files. By combining Systemd and SELinux, we enhance the overall security of our Linux systems. When Systemd starts a service, it can enforce SELinux contexts for that service, ensuring that it runs with the appropriate permissions from the moment it is launched. This integration means that even if a malicious user or process attempts to exploit a service, the SELinux policies restrict the potential damage by limiting what that service can do based on its assigned context. In this section, we will examine how to configure SELinux context within Systemd unit files. The line of code provided is crucial for defining the SELinux context under which a service will operate. Here, we focus on the Nginx web server, and the specific SELinux context we want it to run in is HTTPD. The code snippet begins with the section directive service, indicating that the following configuration will apply to the service itself. Following this, the SELinux context parameter is employed, and it is assigned the value systemu for systemr httpdtb c0.c128. This string is made up of multiple components, each serving a specific purpose in establishing the context. Breaking it down, systemu denotes the user identity, systemr represents the role assigned, httpt specifies the type associated with the web server, while s0 c0.c28 defines the security level and the MLS MCS categories. By integrating this line into the Nginx service unit file, you enforce the SELinux context, which governs the service's permissions, ultimately securing the system from unauthorized access while facilitating the web server's rightful operations. In Systemd service unit files, the line condition security equals SELinux serves a crucial role in ensuring that the corresponding service only starts under the appropriate security context. By specifying this parameter, you create a dependency that guarantees the service will only run when SELinux is enabled on the system. This condition acts as a safeguard against potential misconfigurations or vulnerabilities that could arise if the service were to operate without the necessary SELinux controls in place. By incorporating this line, administrators can enhance the security posture of their applications and services. It prevents services specifically designed to function with SELinux policies from running in environments where they might not be secure, thus avoiding scenarios that could lead to compromised system integrity. This feature highlights the importance of adhering to security best practices, as it efficiently restricts service execution based on the current system state, ensuring that security policies are in effect during the startup process. In summary, condition security equals SELinux is an essential directive for promoting secure and reliable service management in environments utilizing SELinux. The command provided, journalctl SELinux context equals systemu systemr httpt s0, is a powerful tool for filtering logs based on SELinux contexts. In this context, journalctl is the command used to query and display messages from the system journal, which collects logs from various services running on the system. By specifying the parameter SELinux systemu systemr httts0, the command focuses solely on logs generated by processes that operate under the SELinux context related to the HTTP daemon, often referred to as HTTPD. This filtering is particularly useful for system administrators monitoring the web server's activities. By viewing only the log entries that pertain to the specific SELinux context of the web server, one can quickly identify actions taken by the web server process. This targeted approach facilitates the diagnosis of potential issues or unauthorized access attempts, ensuring security measures are effective. The ability to filter logs in this manner enhances the auditing process and provides a clearer understanding of how different processes interact with system resources under SELinux policies. Dbus, another component of the systemd ecosystem, also leverages SELinux for enhanced security during inter-process communication. Dbus facilitates communication between different applications or services. When services communicate over Dbus, SELinux policies control which domains can send or receive messages. This means that you can fine-tune which services can interact with each other, significantly improving your security posture. You can set up SELinux policies within Dbus by using XML configuration files. These files allow you to define permissions for Dbus services to ensure that only authorized services can register themselves or interact with others. For example, you can write a policy snippet that restricts a sensitive service to only communicate with trusted applications. Whether you are managing services, enforcing access controls, or auditing operations, the integration of systemd and SELinux can seem overwhelming at first, but it quickly becomes second nature. The key takeaway here is that with systemd managing the system's services and SELinux enforcing mandatory access controls, Linux becomes a more secure operating environment. By understanding the interplay between these two systems, administrators can significantly improve their server's security, responding more effectively to threats and managing services with greater efficiency. In summary, the combination of systemd and SELinux is a powerful one. It not only enhances security by controlling access, but also provides a sophisticated method for managing services. Integrating these two components into your Linux environment is a step towards a stronger, more resilient system. So remember, whether you're configuring a new service or auditing existing ones, always keep an eye on the SELinux contexts defined in your systemd unit files. Thank you for joining me in this tutorial. I hope you found it informative and engaging. Remember to hit the like button if you learned something new and subscribe for more tutorials like this. Until next time, keep your systems secure and your knowledge growing. When systemd launches a service, it executes the command defined through the exec_start equals configuration entry in the service unit file. By default, a standard domain transition occurs as defined through the SELinux policy. This means that, as part of service management in systemd, SELinux policies play a crucial role in determining how the service interacts with the rest of the system, maintaining a robust security framework. In this tutorial, we will dive deep into the intersection of managing services with systemd and configuring SELinux policies effectively. First off, let's talk about how systemd orchestrates the execution of services. When you define a service in systemd, you encapsulate all necessary commands and parameters in a unit file. This file isn't just a configuration document, it's the manifesto for how your service will operate. The exec start equals line within the unit file specifies the exact command that systemd will run to kick off the service. You can imagine it as the opening act of a concert, where all the other functions and configurations come together to put on a fantastic performance. In this service unit file for a web server, we begin with the directive service, which defines the configuration for the service managed by systemd. The type equals forking option indicates that the service will disassociate from the terminal and continue running in the background. This is typical for daemon processes like web servers. The PID file equals nginx.pid entry specifies where the process ID of the running nginx service will be stored, allowing systemd to track the service's status. Prior to starting the service, exec start pre equals /rbin/rn nginx.pid ensures that any leftover previous runs are removed, preventing potential conflicts with old or stale instances. The command exec start/ua/bin/nginx is the core of the configuration. It executes the nginx web server. In the event of a configuration reload, exec reload equals /bil/hup main_d will send a hang-up signal to the main process, prompting nginx to reload its configuration files gracefully. A key security feature is the SELinux context equals systemu systemr https seer.c128. This explicitly sets the SELinux context for the nginx service, indicating how it should operate within the enforced security policies, thereby minimizing the risks posed by potential vulnerabilities. Lastly, kill signal equals sigquit and timeout stop sec5 manage how the service is stopped, allowing for a controlled shutdown with a grace period, and kill mode equals mixed provides flexibility in terminating the service. The code snippet provided is a modification to the nginx unit file, specifically using the exec start pre directive. This directive is executed before the main process of the service starts. In this particular case, the code is exec start pre +//bin rm.ff/run nginx.pd. Here the command is designed to remove the nginx process identifier file, nginx.pd, located in the /run directory. This file can sometimes remain from previous sessions, leading to issues when attempting to restart the nginx service. By prefixing the command with a plus sign, we instruct systemd to bypass the SELinux context restrictions. This is crucial. If the command were executed with the SELinux context applied, it might not have the necessary permissions to remove the file, which could prevent nginx from starting correctly. Thus, this modification ensures that the cleanup operation is carried out without restrictions, allowing the nginx service to launch successfully. This approach illustrates a balance between maintaining a secure environment with SELinux while providing the flexibility needed for certain administrative tasks. The command we have here is using systemd's systemd-run utility, which allows you to create transient services without the need for a complete unit file. This can be especially handy when you want to quickly run tasks or scripts that need to be managed by systemd, such as running a Python script in a controlled environment. In our example, the specific command is systemd-run-p SELinux context guest u guest or guest t eston 3.6 tmp/py.py. The -p flag is used to set properties for the transient service, and here we are specifically assigning an SELinux context. The SELinux context defined as guest u, guest r, guest t s0 is crucial as it dictates the security permissions under which the Python script will run. By specifying a context this way, you can adapt the security characteristics of the process dynamically, allowing for more flexible and secure executions, particularly in scenarios where the script may require varying access rights during its operation. This approach ensures that your application runs with the appropriate security boundaries defined by SELinux policies, enhancing overall system security while executing specific tasks. Now let's look at the figure. This diagram illustrates the interaction between system components when SELinux policies are enforced within the context of systemd and process management. At the top, we see the SELinux LSM subsystem operating in kernel space. The access vector cache AVC here plays a crucial role, acting as a mediator that checks permissions against the SELinux policy before any specific actions are permitted. The figure delineates the flow of information. Processes and resources are subject to actions that are monitored and controlled by SELinux policies. The process attempts to access a resource, prompting an action. If this action is permissible according to the SELinux policy, it proceeds. Otherwise, it results in a denial that gets logged for administrative review. Moving further, we see the user-space object manager linked to the SELinux policy. This mapping highlights how user-space applications interact with the SELinux policy enforcement. The user access vector cache, user AVC, provides a similar function in user space as the AVC does in kernel space, ensuring that the necessary permissions are in place before any user-triggered actions. The lower portion of the diagram shows how this interaction translates into practical examples, such as writing to a file or launching a service. The arrow pointing from some file to some process indicates that writing operations are governed by the Linux kernel and controlled by SELinux. Similarly, the process of launching a systemd service is illustrated. The figure emphasizes that while SELinux facilitates the enforcement of policy rules, the actual execution and initiation of system services falls under the management of systemd itself. By visualizing these relationships, the figure effectively conveys how SELinux integrates with process actions and resource access, ensuring that all interactions align with defined security policies. The provided code snippet is a directive within a systemd service unit file, specifically under the unit section. It utilizes the condition security directive, which serves as a conditional check to ascertain if certain security features are active on the system. Here, focusing on SELinux, Security Enhanced Linux. By defining condition security equals SELinux, you are instructing systemd to only start the corresponding service if SELinux is enabled and operational. This approach ensures that critical services do not initiate unless the appropriate security context is established. If SELinux is not active, systemd will withhold the service's execution, thereby preventing potential security risks that could arise from running a service in an insecure environment. This conditional safety mechanism streamlines system management by enforcing a baseline security requirement, ensuring that services adhere to the security policies you've enforced. This adds an additional layer of protection to your system, reflecting a proactive approach to system and service management that prioritizes overall security integrity. The command journalctl-b grep-i SELinux is a powerful tool for examining logs related to SELinux. The journalctl command is used to query the logs recorded by the systemd journaled service, which maintains logs from the earliest boot session onward. By using the -b flag, you're specifically filtering the logs to only display information from the current boot session. This reduces the volume of output and allows you to focus on issues that have occurred since the system was last started. To further refine the search results, the output of journalctl is piped into grep-i SELinux. This part of the command searches through the logs for any entries that mention SELinux, regardless of case, due to the -i flag, which makes the search case-insensitive. By doing this, you can quickly locate relevant SELinux policy violations, which is essential for troubleshooting related issues. This command effectively helps system administrators and developers understand SELinux denials in their service logs. Now let's have a quick laugh, shall we? Why did the SELinux policy break up with the command? Because it just couldn't handle all the unrestricted access. All jokes aside, working with SELinux and systemd requires patience and practice. Understanding the key components like unit files, SELinux policies, and the interaction between them will significantly enhance your capabilities to manage services effectively. Remember, if discovering systemd feels like trying to assemble IKEA furniture without the instructions, don't worry, you're not alone. Embrace the complexity and keep exploring, as mastering this can be rewarding. In conclusion, the fusion of managing services with systemd and SELinux policies is a powerful approach to ensuring your Linux environment remains robust and secure. By carefully configuring unit files and understanding the transitions and contexts, you can leverage these technologies to create a comprehensive and secure service management strategy. Happy coding! In the previous chapter, we covered some SELinux-aware applications, which are designed to interact with the SELinux subsystem to enhance security. This time, we're diving into SEPostgreSQL, a fascinating extension of PostgreSQL that integrates with SELinux, giving us a powerful tool to manage database security. So grab your notepad because we're about to unlock some advanced security techniques. First, let's get our bearings. SEPostgreSQL, or Security Enhanced PostgreSQL, is an enhancement of the PostgreSQL database management system that utilizes SELinux features. PostgreSQL, as many of you know, is a robust relational database widely used for its performance and standards compliance. But with SEPostgreSQL, we're adding an additional layer of security that isn't just about the database itself, but about the entire environment in which it operates. The core idea behind SEPostgreSQL is the use of SELinux's labeling mechanism. In SELinux, every process and resource can be tagged with a security label. SEPostgreSQL applies this concept to database objects, enabling fine-grained access controls within PostgreSQL. This allows us to enforce security measures that go beyond what standard PostgreSQL access controls provide. Think of SELinux as the stern but fair guard at the door of our database. Only the right labels and credentials can pass through. Now you might be wondering, what exactly do we gain from integrating SELinux with PostgreSQL? Well, it allows us to define complex security policies based on labels associated with database entities. This can include tables, columns, and rows, even down to user-specific access controls. Imagine managing sensitive data without worrying about unauthorized access. It's like having a built-in bodyguard for your data. Let's lay out some of the key components of SEPostgreSQL. First, we have security labels, which are attached to database objects. These labels typically contain three elements: the SELinux user, role, and type, followed by the sensitivity level and category. This tagging allows SELinux to determine access rights dynamically. For example, if a table is labeled as SGS School Secret Table T, it can only be accessed by users or processes that possess the appropriate SELinux context. The first line of the code retrieves the security context of the current session by using the function sepgsql_getCon. This function is crucial for understanding the security environment in which your database operations are being executed. It provides insights into the labels assigned to sessions, helping maintain a secure database setting. Next, the code sets a specific security context for the current session using sepgsql_setCon, desired context here. By specifying a context, you can control the permissions and restrictions for actions within that session. This is particularly important for ensuring that users operate within their designated boundaries, akin to ensuring that every user knows their limits within a shared space. Lastly, the command sepgsql_restoreCon relabels all objects in the database back to their default security labels. This function is essential for maintaining a consistent security state, especially after changes have been made to labels or contexts. By restoring the default settings, you ensure that the database returns to a secure, known state, safeguarding against unauthorized access and maintaining the integrity of user interactions. In this tutorial, we focus on implementing security labels in a PostgreSQL database to safeguard sensitive information. The code provided demonstrates how to assign a security label to a specific column in the TB users table, particularly the email column. The command security label on column tbusers.email is systemu object r sepgsql table ts0901 specifies that this column is associated with a certain security context. The security label is crucial for enforcing access control policies. In this instance, the label systemu object r all table sc901 is applied, indicating that the email field contains sensitive data, which falls under strict management. This means that if a user tries to access this information without the necessary permissions, the system will deny their request. This enforcement is akin to using a security badge. Only those who have been granted the appropriate access can retrieve or view the labeled information. By integrating this security labeling into our database design, we enhance the protection of personally identifiable information, PII, and ensure compliance with privacy regulations. We also take advantage of multi-category support, MCS, and multi-level security, MLS, which are powerful features of SELinux. MCS allows you to assign different categories to different users and resources. For example, this way, you can segregate access to certain types of data based on user roles or data sensitivity. It's akin to having a VIP section in a club. Only those on the guest list get in. To implement this, you can set up categories for users when they log into PostgreSQL. By changing their context using functions like SELinux-Secured, you can adjust their access on the fly depending on their roles, enabling them to work with various data sensitivity levels as needed. Now let's look at the figure displayed. This diagram represents the relationships between various entities in a SEPostgreSQL setup, emphasizing the role-based access control schema. Each box pertains to a specific entity in the database, including user, group, tenant, and role, along with their corresponding attributes. Starting at the top left, we have the user entity, which includes the fields ID and email. The ID serves as the primary key, uniquely identifying each user. This entity is crucial as it is linked to both user group and user role, indicating the user's association with specific groups and roles within the system. Next, we move to the user group entity, which features an ID, user ID, and group ID. The user ID field establishes a connection with the user, linking them to respective groups. This shows how group membership can enhance or restrict user permissions within the database. On the right of the diagram, the role entity contains an ID and name, defining the various roles that can be assigned to users. This ties into the user role entity, where each record links a user to a specific role via user ID, tenant ID, and role ID. This structure supports the implementation of granular permissions, allowing tailored access based on roles. The tenant entity sits at the bottom with an ID and name. It signifies separate multi-tenant environments within the database. The connections to both the group and user role entities illustrate the hierarchy of access rights across different tenants, ensuring that users can only access data that they are explicitly permitted to view. Lastly, the group entity features an ID, name, and tenant ID. This relationship enables groups to be defined within the context of specific tenants, further segmenting access controls. Each entity is interconnected through primary and foreign key relationships, highlighting how data integrity and structured access controls can be maintained in a SEPostgreSQL environment. To start, you need to check if your PostgreSQL databases are up and running. This can be accomplished with the command psqlu postgresl, which connects to the PostgreSQL server using the Postgres user and lists all available databases. This quick verification step ensures that your PostgreSQL instance is operational before proceeding with further installations. Once you've confirmed the databases are live, the next step is to install the SEPostgreSQL module. On XenOS, this is done using the command yum install PostgreSQL contrib. This command installs the additional PostgreSQL packages, including the necessary features and modules that enhance functionality and performance, such as SEPostgreSQL. After the module installation, you need to enable it in the PostgreSQL configuration. Open the PostgreSQL configuration file and modify the shared preload libraries setting, adding SEGSQL to it. It's crucial to remember that any changes made to this parameter will require a restart of your PostgreSQL service for them to take effect. This series of steps ensures that you have SEPostgreSQL properly installed and configured. Before wrapping up, remember to regularly check the SELinux logs. They provide valuable insights into any access denials and can help fine-tune your security policies. If you encounter any access issues, the logs will be your friend, showing you who was denied and why. It's like having access to the bouncer's book, helps you understand the guest list. In conclusion, SEPostgreSQL is a brilliant security enhancement that harnesses the power of SELinux to provide a much tighter security model within your PostgreSQL databases. It's like equipping a fortress with the latest high-tech security features while also training your guards. They'll be standing watch, ensuring only the right folks get in. So if you're dealing with sensitive data and want a stronger security framework, give SEPostgreSQL a try. Let your data stay protected while you focus on building great applications. Happy querying, and keep the data safe. When we use the SEPostgreSQL module in PostgreSQL, all database sessions need to have a security context associated with them. This means that every time a user establishes a connection to the database, it's vital that their session is linked with a specific security context. Why? Well, this connection ensures that every access is scrutinized based on the rules of the SELinux policy, enabling more powerful access control mechanisms. To put this into context, think of it like having a VIP pass to a concert. When you approach the entrance, security needs to check if you have the right pass to enter. If you don't, you simply can't go in. This mechanism is effectively what SEPostgreSQL does with database access. It uses security categories and contexts to control access. While local communications via Unix domain sockets are straightforward because the context is inherently available, the scenario becomes trickier with network sessions. Without a proper security context for such sessions, interactions with the database could lead to failures. Now let's look at this figure, which illustrates the interaction between processes, SELinux, and resources. On the left side, we see the process component, representing an active process within the system. This process initiates requests for accessing various resources, which could be files, directories, or other types of data essential for its function. As the process interacts with SELinux, the flow of information is depicted with arrows indicating the communication between these two entities. The arrows suggest that the process sends requests to the SELinux module, where SELinux policies are evaluated. This evaluation is crucial as it determines whether the requested actions by the process comply with predefined security policies. Inside the SELinux module, we see the AVC component, which stands for Access Vector Cache. The AVC acts as the decision-making intermediary, processing the incoming requests and comparing them against the SELinux policies. This is an essential step, as it ensures that only authorized actions are permitted, thereby maintaining the integrity and security of the system. The figure further illustrates a decision point indicated by a diamond shape labeled Access Granted. If the policies allow the requested action, the process will receive permission to access the desired resource, shown by the green arrow leading to the resource on the right. However, if the request does not align with the established policies, the red arrow indicates a denial, emphasizing that improper accesses are blocked, thereby protecting the resource from unauthorized actions. This visual representation succinctly encapsulates the flow of control in SELinux, highlighting the critical roles of processes, policies, and the AVC in ensuring secure access to system resources. This reflects the need for a compliant security mechanism in place. So how do we overcome this? The common approach involves implementing labeled IPsec, which ensures a secure and controlled communication medium. Let's dive deeper into labeled IPsec. With labeled IPsec, each packet that traverses the network is tagged with a security label, similar to how files might be labeled confidential or top secret. This added layer of security helps ensure that only authorized sessions can initiate communication. But what if you can't set up labeled IPsec for some reason? That is where NetLabel comes into play. NetLabel allows us to establish a fallback labeling mechanism. It associates a label with traffic based on the source address. A neat workaround for those tricky scenarios where setting up a full labeled network is overkill or not feasible. The SEPostgreSQL module provides several functions for your use. One such function, SETSQL-getCon, retrieves the current context of your session. Conversely, if you have the appropriate permissions, you can use SIP-GSQL-setCon to modify the session context. This is an example of how you can implement these functionalities in practice. This command retrieves the current security context for the active session. If your context is set up correctly, it should return a string similar to this. That's your current walking permit into the concert of database privileges. If you ever need to bring everything back to its default state, there's also the SEF-GSQL-restoreCon function, which effectively relabels the session context back to its original setup. This can be likened to a reset button where things go back to their assigned states. In addition to these, you may also utilize SEP-GSQL-MC-strands-in and SEP-GSQL-MC-strands-out to work with the MC-strands daemon, which translates human-readable sensitivity ranges into the raw format used internally, and vice versa. This brings additional flexibility and power to how you manage and interact with sensitive data in your database. Now let's look at this figure, which illustrates the evolution of security context coverage in the LAP software stack. specifically focusing on SELinux integration. The figure is divided into 3 sections: at the past days, nowadays, and in the future. In the first section, at the past days, we see a classic representation of a web application stack featuring the application AP server at the top, followed by the web server, database server, and kernel layers. Notably, this configuration shows the database server running PostgreSQL without any additional security measures from SELinux. Here, the kernel layer is solely represented by SELinux, which suggests limited enforcement of security policies across the stack. Shifting to the nowadays section, we observe significant changes. The inclusion of SELinux alongside the web server and the shift to SEPostgreSQL for the database server is crucial. This indicates a more robust security posture, where SELinux provides enhanced security for both the web and database components. The AP server still supports traditional frameworks like PHP and Tomcat, while the web and database layers now leverage SELinux for improved data protection and context management. Finally, the In the Future section envisions a further evolution of the stack. It anticipates even deeper integration of SELinux across all layers, ensuring comprehensive security coverage for both the AP server and the database server. This progression highlights the ongoing commitment to securing web applications through the effective application of security contexts, enabling organizations to protect sensitive data with increased granularity. This figure succinctly captures the advancements in security measures within the LAP framework, reinforcing the importance of understanding and applying these mechanisms in today's data-driven environment. Virtualization is a core concept that plays a significant role in many infrastructure service designs. It originated in the early 1970s as a means of isolating workloads and abstracting hardware dependencies. Since then, virtualization implementations have grown tremendously, becoming indispensable in modern computing environments. As we explore virtualization, one key aspect to consider is how we can secure these environments, especially given the risks they can pose. Enter SELinux, or Security Enhanced Linux. In this video, we'll dive into how SELinux can enhance the security posture of virtualization. Before we delve deeper into SELinux and virtualization, let's lay the groundwork by understanding what virtualization actually entails. In simple terms, virtualization allows multiple virtual environments to operate on a single physical machine. Each of these environments can run its own operating system, potentially leading to increased resource utilization and improved cost efficiency. Virtualization allows for the creation of virtual machines, VMs, that abstract hardware, thereby allowing different operating systems to run on the same physical server. With this abstraction comes a host of benefits: centralized management of resources, simplified scaling, and even enhanced security when executed correctly. However, with great flexibility comes great responsibility, specifically the need for security. Since multiple VMs share the same hardware, a breach in one VM could potentially impact others or even the host system. Now, let's look at this figure, which illustrates the architecture of various virtualization hosts and their interactions. At the top of the figure, we see several management tools: Virsh, Virt Manager, Virt Install, and Virt Viewer. These tools are essential for coordinating virtual machine operations, enabling users to create, configure, and manage virtual environments effectively. Beneath these management tools, we find the Libvirt daemon, which serves as a crucial middleware component. It manages the interaction between the management applications and different hypervisors. Each host is associated with its respective hypervisor, as displayed in the figure. Host A utilizes the QEMU KVM hypervisor, running 2 guests, guest A1 and guest A2. This illustrates the scalability of virtualization, as multiple virtual machines operate on the same physical host while remaining isolated from one another. Moving down to host B, it utilizes the Xen DOM0 hypervisor, which also supports 2 guests, guest B1 and guest B2. This setup highlights the flexibility of virtualization technologies to accommodate varying architectures. Each host operates within its security confines, and policies can be enforced at this level to restrict access and manage resources efficiently. Finally, we see host C, which employs a proprietary hypervisor and similarly runs 2 guests, guest C1, and guest C2. The diagram conveys how different hypervisors can be used interchangeably to serve various virtual machines while still allowing for centralized management through Libvirt. This figure effectively represents the layered structure of virtualization environments, demonstrating how SELinux can fit into each level by enforcing mandatory access control policies to bolster security across different hosts and guests. Let's dive deeper into how this works within a virtualization context. One of the notable features that SELinux offers is its ability to isolate virtual machines through type enforcement and role-based access controls. Each VM can be given its domain and labeled accordingly. For instance, a VM running a web server can be assigned different labels and policies than one running a database. By doing so, SELinux ensures that these different workloads do not interfere with one another, effectively increasing the security of your infrastructure. Here's a quick look at how SELinux is structured in this context. SELinux employs a concept called SVirt, which stands for Secure Virtualization. With SVirt, both the host and guest domains are assigned security labels that control access to various system resources. For example, the hypervisor software running your virtual machines will use a distinct domain, such as Virtvirt. But what about the different types of VMs you might run? SELinux categorizes the various interactions that these VMs can have. Here's how it often breaks down. SVirt. This is a generic label for guest VMs that operate without needing to interact with the host beyond basic operations. SVirt-QEMU-Net. This label is designed for guests using QEMU network capabilities, allowing them to engage in network interactions. SVirt-LXC-Net. This label is specifically for containerized guests, differentiating them from standard VMs. These labels play an essential role in defining what a VM is allowed to access and interact with. The provided command uses grep to search for specific indicators of hardware virtualization capabilities within the flatproc CPU info file. The flags SVM and VMX correspond to the two main virtualization extensions provided by AMD and Intel processors, respectively. When executed, the command scans the processor information listed in proc CPU info, and if hardware virtualization is supported, will display lines containing either SVM for AMD processors or VMX for Intel processors. By running this command in a terminal, you can quickly identify if your system's CPU has the necessary features to support virtual machines, which is essential for setting up secure virtual environments. If the command returns matching lines, it indicates that your hardware can handle virtualization without significant limitations. Conversely, if no output appears, your system may lack these features, which could hinder the deployment of effective security measures, such as those enforced by SELinux in virtualized environments. Understanding these capabilities is crucial for configuring secure and efficient virtualization setups. While SELinux provides robust frameworks for securing virtualization, it's not a catch-all solution. It does require careful configuration. Misconfigured SELinux booleans could inadvertently allow more access than intended. For example, enabling the staff useVirt boolean allows members of the staff T-user domain to manage virtual machines, which may increase risk. Thus, understanding how to manipulate and monitor these settings becomes a vital part of an administrator's role. For this reason, it's paramount to strike a balance in your SELinux settings. Always perform a risk assessment before deciding to enable or disable specific SELinux policies. Remember, even a small error in privilege management could lead to vulnerabilities. As we wrap this exploration of SELinux-secured virtualization, it's clear that while virtualization offers us unparalleled efficiency, it also introduces a unique set of risks. SELinux serves as a critical component in ensuring we can exploit the benefits of virtualization without compromising security. With its dominant access control features, SELinux enables a multifaceted security model that protects both the host and its guest systems. So, whether you're a seasoned administrator or a budding enthusiast, remember that your approach to virtualization must incorporate robust security measures like SELinux. In the world of IT, securing your virtual environments is not just a best practice, it's a necessity. Thank you for joining me today, and I hope you got a clearer perspective on how SELinux enhances the security of virtualization. Don't forget to subscribe for more content on maximizing your IT skills. And remember, the only bad question is the one you don't ask, especially when it comes to security. The Libvirt project offers a virtualization abstraction layer through which administrators can manage virtual machines without direct knowledge of or expertise in the underlying virtualization platform. This means that Libvirt provides a user-friendly interface to control complex systems like QEMU, KVM, and Xen, enabling users to leverage virtualization technology without needing to dive deeply into the intricacies of the underlying hypervisor. To enhance this usability and security, particularly in sensitive environments, the integration of SELinux, Security-Enhanced Linux, support is crucial. SELinux provides a robust mechanism for enforcing access controls, enabling administrators to define and enforce policies that restrict what actions are permissible by any process running on the system. This is especially important in a multi-tenant environment where multiple virtual machines may be running on a single physical host, potentially exposing sensitive data if one virtual machine can access another's resources. Leveraging SELinux, we can control which users and processes have access to various resources, significantly reducing the attack surface. In this XML snippet, the SELabel tag is utilized to define the security context for a virtual machine within Libvirt. The attributes within this tag indicate that it employs SELinux for security enforcement, with the model being explicitly set to SELinux and the relabeling functionality enabled. This means that the security labels associated with the virtual machine can be dynamically managed based on changing contexts. The nested label element specifies the SELinux context for the guest, represented as system-u, system-r, svirt-t, c533, c565. Here, system-u denotes the user, system-r indicates the role, svirt-t defines the type assigned to the guest process, and the final components represent the level and categories for fine-grained access control. Additionally, the image label element provides the security context for the guest's disk image, labeled as system-u, object-r, svirt, image tiro, c533, c565. This context ensures that the resources used by the virtual machine, such as its disk image, are also protected under SELinux policies, allowing for consistent enforcement of security measures across all operations conducted by the guest. By embedding these security labels within the guest's definition, Libvirt can maintain strict and effective control over access rights and actions. Another key feature of SELinux, in combination with Libvirt, is the multi-category security, MCS. MCS allows administrators to assign a pair of categories to each guest. This strategy offers enhanced isolation, enabling a larger number of guests to coexist safely without the risk of cross-communication or data leakage. Let's consider a real-world example. Say you are running 90 different guests, and you assign each a single category. You would be limited to 90 guests before they would start overlapping, which, as you might guess, is a self-defeating strategy for isolation. However, each guest can have a dual category pair assigned. If we were to calculate this, the number of uniquely assignable guest pairs becomes quite large. By using combinations, we find that this can support over 4,000 different guest setups. This ensures that even in a confined category space, the operating capabilities are maximized while still maintaining strict isolation. When a new guest virtual machine is created, it's crucial to monitor its operational status and security context. The command ps-efz grep QEMU system x8664 serves this purpose by listing all currently running processes related to QEMU, which is the underlying virtualization technology used for handling virtual machines on a Linux system. The ps-f portion of the command retrieves an exhaustive snapshot of all running processes along with their associated details. The -z flag adds another layer of information by displaying the SELinux context for each process. This is particularly important in environments where security is a priority, as it helps to ensure that the correct security policies are applied to your virtual machines. By piping the output through grep QEMU system x8664, we filter the process list to focus solely on QEMU instances, thereby allowing users to easily verify the status and security context of their guest machines. This command is essential for administrators seeking to maintain security and performance while managing virtualized environments. In this section, We focus on modifying the security label of a virtual machine guest by using a specific XML entry. The code provided demonstrates how to define a static security label for a guest, which is crucial for maintaining consistent security policies. The seek label element defines the security context that will be applied to the guest. The type attribute is set to static, indicating that the security label will not change dynamically. This is particularly advantageous for administrators who want to ensure that the guest consistently operates under the same security context, reducing the risk of unexpected behaviors that can arise from automatic label assignments. The model attribute specifies that SELinux is the security model in use, which is widely known for its robust access controls. The relabel attribute set to yes confirms that SELinux is authorized to modify the guest's security label. Within the label tag, you find the specific SELinux label, which comprises the security context parameters. This particular label, System U, System R, SVirt, TCG, C1223, C1E4, encapsulates user role type and level information that governs the access permissions and protections for the guest environment, ensuring that it operates securely within the host system. In this configuration, a disk is defined for a virtual machine using XML syntax, which is common in virtualization technologies like Libvirt. The disk element specifies the type of disk as a file, indicating that the disk image resides in the file system. The driver tag defines the driver to use, in this case, QEMU, and the type of disk image format, which is set to QCOW2. This format is known for its support of features like snapshots and efficient disk space management. The source tag specifies the path to the disk image file, located at /var/lib/libvirt images test.qcow2. The target tag outlines the device attribute, specifying that this disk will be accessible as HDA on the ID bus. The address element further identifies the disk's location in the virtual hardware architecture. A crucial aspect of this configuration is the seek label element with the attribute relabel equals no. This setting ensures that the SELinux context for the disk remains unchanged during usage, thus avoiding unnecessary relabeling operations. This allows for efficient read and write access while maintaining security, particularly in environments where multiple guests need to share resources securely. Moreover, implementing SELinux with Libvirt can help mitigate performance issues linked to virtualization. By properly configuring SELinux contexts and ensuring they correspond appropriately with the virtualization framework, such as KVM or QEMU, you are ensuring that access control is both seamless and transparent. Keep in mind that configuring SELinux properly requires continuous adjustments and monitoring. As virtualization environments grow and change, so too will the demands placed on your SELinux policies. It is wise to have a robust monitoring and auditing system in place to catch potential breaches or configuration errors before they escalate. In conclusion, the integration of SELinux with Libvirt provides an indispensable layer of security for administrators. By utilizing the powerful capabilities of SELinux, such as type enforcement and MCS, Libvirt can operate more securely, protecting sensitive data while enhancing the overall management experience. Embracing these features may require additional administrative overhead at first, but the benefits in terms of security and stability are well worth the effort. Now, as we all know, a safe virtualization environment is a happy virtualization environment. Until next time, stay secure and keep exploring the capabilities of SELinux and Libvirt to protect your cloud resources. The Xen project is a Linux Foundation project that maintains the Xen hypervisor. It's a broad project managing various software titles related to security and virtualization, but our focus here is primarily on the Xen hypervisor itself. Now let's break down what this hypervisor does and introduce you to the exciting world of Xen security modules, or XSM. Get comfy, grab your coffee, and let's dive into it. First things first, what exactly is the Xen hypervisor? Well, think of it as the middleman between your virtual machines and the physical hardware they run on. Unlike other virtualization solutions like QEMU or KVM that work as processes within a Linux environment, Xen sits directly on top of the hardware. This distinct architecture means that when you're using Xen, you're not actually seeing various virtual instances running as traditional processes. Instead, You're interfacing with the hypervisor through specific Xen commands and APIs. You might say it's like the stealthy ninja of virtualization, powerful yet invisible. An essential concept to understand in Xen is the terminology it uses. In the realm of Xen, we refer to virtual machines as domains. This might cause a bit of confusion since domain can also pertain to SELinux types for running processes. However, we'll stick with the term guest when discussing user data or processes to keep things clear. Every Xen installation has at least one virtual domain known as Domain 0 or DOM0 for short. Think of DOM0 as the VIP guest in this virtual party. It not only manages the system, but also runs essential services like the Xen daemon, shortened to Xend. So if you're planning on launching other virtual environments, you'll be doing it through this privileged guest. The other domains are the regulars, known as DOM-U, which are unprivileged. It's like having a party where there's one special guest, DOM0, who controls everything while the other unprivileged guests hang out and enjoy the party. Now let's look at this figure, which illustrates the architecture of the Xen hypervisor. At the top, we see the classification of virtual machines, VMs, starting with VM0, also known as DOM0. This is the domain responsible for managing the hypervisor and serves essential system services, including the task scheduler, domain and event management, and the Xen security model. The DOM0 kernel functions as the bridge between the physical hardware and the virtual machines, providing native drivers for hardware interaction. Moving on to the subsequent sections of the figure, we can notice VM1, VM2, and so on, representing the guest domains known as DOM-U. Each of these virtual machines runs its own applications and guest operating systems, allowing for independent operation. This structure facilitates the effective separation of workloads, where resources can be allocated dynamically based on the requirements of each guest domain without interfering with one another. At the bottom of the figure, we see the host components, including I/O, memory, and CPU resources. This layer is crucial as it indicates the physical resources managed by the Xen hypervisor. The figure also highlights operational elements such as the scheduler memory management unit, MMU, timers, and interrupts, which are vital for efficient resource management and task scheduling between the DOM0 and the various DOM-US. This architectural overview sets the foundation for understanding how Xen orchestrates multiple virtual environments on a single host system. Having successfully installed Xen, it's time to shift gears a bit and explore the security aspects of this hypervisor. Here, XSM comes into play. Xen security modules represent a crucial part of the Xen hypervisor's security framework. Borrowing concepts from Linux security modules, XSM enables us to define permissions and establish controls over actions between and within guest domains. XSM consists of a single module called XSM Flask, which is a take on the Flux Advanced Security kernel, similar to how SELinux operates. With XSM Flask enabled, you can meticulously control interactions not just between Xen guests but also between those guests and the Xen hypervisor itself. You can manage access to hardware resources, control privileged operations, and much more. This is where you truly start to appreciate the backbone of security in the Xen environment. Because, let's face it, an unprotected party is just waiting for trouble. Now, let's look at the figure, which provides a detailed overview of the Xen virtual environment architecture. The diagram shows two compute nodes, each running multiple guest virtual machines, VMs, managed by the Xen hypervisor. The guest VMs are categorized by color, with blue representing the current tenant and gray indicating other tenants. This visual distinction helps clarify which VMs are directly associated with your environment. Inside each compute node, we see the architecture's core components, including the DOM0, which serves as the management domain for the hypervisor. DOM-0 interfaces directly with the hypervisor, allowing it to manage resources and communicate with the VMs. Notice that both compute nodes contain a VMI engine housed within DOM0, which plays a critical role in the security architecture by ensuring effective monitoring and management of VM interactions. Moving to the right side of the figure, we observe the cloud controller, which operates as a central command point for managing tenants and security policies within the cloud environment. The controller is connected to a monitoring backend, facilitating oversight and coordination between tenants and the security measures in place. This connection is crucial for establishing a secure cloud setup, as it allows the controller to enforce policies and monitor compliance effectively. The arrows in the figure indicate the flow of communication and control commands. For instance, the connections between the compute nodes and the cloud controller highlight how the system maintains an organized and secure environment. It is also essential to pay attention to the MSSP, Managed Security Service Provider, which is a vital component for external management and monitoring, providing additional resources for security and operational oversight. Overall, this figure encapsulates the intricate relationships and functionalities within the Xen framework, showcasing how virtual machines interact under a unified security policy and management system. By understanding this architecture, you can better appreciate how to configure and enforce security settings effectively in your cloud environment. In this tutorial, we focus on the command used to label a PCI device for unprivileged guest access within the Xen environment. The command flask label PCI 00002.0 system u object r nicdevt does more than just assign a label. It establishes security boundaries that protect your system while allowing specific functionality. The first part of the command, flask-label PCI, directs Xen to utilize the Flask security framework to manage labeling. The identifier 000.0 specifies the exact PCI device you intend to manage, ensuring that only this device is affected by the following security policies. By clearly indicating the device, you help maintain both security and performance by avoiding unintended consequences for other components. The second segment, System U Object R nicdevt, sets the security context for the PCI device. Here, System U identifies the user, while Object nicdevt specifies the role and type associated with the device. This combination establishes a controlled environment, ensuring that unprivileged guests can access the device without compromising the integrity of the system. Ultimately, this enhances security while still granting necessary functionality. In summary, Understanding Xen and XSM is all about knowing the relationship between the hypervisor, virtual guests, and security measures that keep everything in check. Xen acts as the powerful mediator, orchestrating operations between hardware and virtual machines, while the XSM ensures only the right guests gain access to the right resources. So whether you're deploying a new guest or fortifying your Xen environment's defenses, always remember that security isn't just an option, it's a necessity. If you found this overview helpful, don't forget to hit that like button and subscribe for more technical insights. Catch you at the next session. Xen is an innovative hypervisor that provides powerful virtualization capabilities, and one of its standout features is the ability for administrators to create and utilize their own custom security policies. This is made possible by a framework known as Xen Security Modules, or XSM. As we dive into this topic, we'll explore how to apply these custom XSM policies effectively, ensuring that our virtual environments remain secure and tailored to our specific needs. First things first, let's understand what exactly we mean by custom XSM policies. The default policies provided by Xen are generally robust, but they may not fit the unique requirements of every environment. That's where custom policies come into play. By allowing administrators to design their own policies, Xen enables us to define access controls and restrictions that align perfectly with our operational needs. Now let's look at this figure. The visual representation illustrates the architecture of the Xen virtualization system, highlighting the relationships between various components. At the core of the diagram, we find the various rings, with ring 0 at the center. This ring is the most privileged level, allowing direct access to hardware and system resources. As we move outward, we encounter rings 1, 2, and 3, each representing progressively less privileged levels. This layered approach enhances security and stability within the system. To the left of the rings, we see the management domain. This domain is responsible for several critical tasks, such as virtual machine management, HTTP interface handling, and access to the Xen hypervisor. The connections between the management domain and the rings illustrate how high-level operations interact with the underlying architecture, to facilitate virtualization tasks smoothly. On the right side, the figure outlines the flow of interaction between components. It starts with the user application, which operates under an unmodified Application Binary Interface, ABI. The application communicates with user domains, which can include guest operating systems and modified code bases. The user domains rely on hypercalls into the Xen Virtual Machine Monitor, VMM, for privileged operations, showcasing a crucial interaction point. The figure also underscores the role of the Xen hypervisor, detailing its responsibilities in memory management, CPU state registration, and device I/O operations. The arrows indicate that specific privileged instructions can be executed by the hypervisor, leading to hardware traps and interactions with the underlying x86 hardware. This layered structure not only optimizes resource management, but also ensures security through separation of privileges across different rings and domains. Once you have determined the desired outcome for your new policy, the next step is to revise the policy files to align with your requirements. After making the necessary adjustments, it is important to rebuild the policy. This can be accomplished using a simple command. Upon building the policy, a new file called xenpolicy-413.1 will be created, reflecting your customizations. What's next? We need to load this newly created policy into the Xen hypervisor. This is done using the following command. This command is straightforward. It basically tells Xen to take your freshly baked policy and start enforcing it. The actions and access controls defined in your custom policy now come into play, modifying how Xen and its guests interact with resources and each other. After you have tested the new policy and feel satisfied and confident with your configurations, it's advisable to take further steps to secure it. To make sure that your custom policy is automatically recognized during the next system boot, you should copy it to the /boot directory. This ensures that your tailored security measures remain effective even after reboots. Additionally, you may find yourself in a situation where you need to check the current status of your XSM policy. Luckily, Xen offers tools that are similar to those used in SELinux for this purpose. One useful command is flask-get-bool, which allows you to view the current state of the security booleans. This command will show you all the current states of Boolean values defined in your policy, giving you insights into the active permissions and restrictions. When discussing permissions, it's essential to highlight that, similar to SELinux, XSM utilizes a label-based access control system. This feature becomes particularly significant when a new virtual guest is created within the Xen environment. The labels designated for each guest instance play a crucial role in determining the resources they can utilize and the actions they are permitted to take. For instance, the DOM-U type designates unprivileged guests, whereas the DOM-0 type is reserved for the privileged management domain. To set a security label for a guest, you need to edit its configuration file found in //etc/xen. You can accomplish this by adding a specific line to the file. This configuration ensures that your DOM-U guest adheres to the restrictions defined in the isolated policy, enhancing its security posture against untrusted interactions from other guests. The XSM framework has a significant capability in managing permissions for hardware resources. By assigning specific XSM types to certain PCI devices, it allows control over which unprivileged guests can directly access those devices. This feature is especially useful in situations where certain guests need to interact directly with hardware components for enhanced performance, like in cases of GPU pass-through or when using network interfaces. If you need to assign a specific type to a PCI device, the flask label PCI command can be utilized for this purpose. Doing so marks the device for pass-through access, allowing specified guests to utilize it directly. This level of control opens up new possibilities for performance tuning while maintaining security. Although we have placed significant emphasis on creating and implementing custom policies, it is just as important to consistently monitor and evaluate their impacts. Similar to how we would track the logs produced by any security system, overseeing XSM entails examining its log entries as well. Utilizing commands such as xldsgig can help in reviewing the logs that pertain to the behavior and decisions of XSM. This log will provide insight into granted and denied actions, helping you fine-tune your policies further. Lastly, remember that applying custom XSM policies don't just provide security compliance. They also enhance operational efficiency by allowing resources and permissions to be tailored to the specific needs of your virtual environment. In summary, applying custom XSM policies in Xen allows for a great deal of flexibility and security robustness. By adjusting default policies, building your own, and leveraging Xen's labeling mechanisms, you can ensure that your virtual infrastructure remains secure. Continuing to monitor and adapt your policies in real time makes this a dynamic process that can greatly enhance the security and efficiency of your operations. And who doesn't like their virtual machines to be as secure as possible? The world of virtualization is ever evolving, folks, so stay curious, keep experimenting, and above all, secure your environment. SELinux, short for Security Enhanced Linux, is an integral part of the Linux operating system designed to enforce a security policy on processes. It plays a pivotal role especially in containerized workloads, where the essence of using containers is about deploying applications in isolated environments. Today, we'll dive into the fascinating world of SELinux and see how it contributes to securing containerized workloads, ensuring that those untrusted containers can't escape their constraints or access resources that they shouldn't interact with. When you think of containers, imagine them as portable boxes that house an application and everything it needs to run. However, there's a catch. These containers need to operate securely within the confines of their environment. SELinux acts as a vigilant guard, making sure that each container respects its own boundaries and interacts only with the resources it's allowed to. This is like a bouncer at a club, ensuring that everyone stays in their designated area and prevents any unruly guests from wandering into restricted zones. Now let's look at the figure displayed here. This listing illustrates a code snippet that provides a practical example of how to add SELinux attributes to the SELinux Policy Graph database. The snippet begins with a command to load a CSV file, specifically targeting the attributes.csv file. The header information is incorporated to facilitate the clear association of the data being processed. Moving on to the match clause, it identifies specific types within the graph database by correlating them with the types defined in the loaded attributes. This step is crucial, as it matches the existing types in the policy with those represented in the CSV file to ensure that any attributes being added align correctly with established processes. The final part of the script involves the set command. This command is used to modify the existing attribute vector for the matched type by incorporating the attributes defined in the CSV file. The use of apoc.call.union ensures that any new attributes are effectively combined with the existing ones, allowing for an expanded set of permissions or capabilities for the SELinux context. Overall, this figure succinctly encapsulates the process of enriching the SELinux policy graph with attributes that dictate the permissions of various processes, emphasizing the mandatory nature of SELinux policy enforcement. In the provided command, podman run-name nginx test-p8080 nginx, we are launching a new instance of an nginx container using podman. The run command signifies that we want to create and start a container. The flags -d and t are used to modify the behavior of the container. Specifically, -d runs the container in detached mode, meaning it will operate in the background. The -i option allows us to maintain an interactive session, while -t allocates a sudo tty, which enables terminal emulation. The name-next test portion of the command assigns a readable name to our container, making it easier to manage than using the automatically generated container ID. The -p8080 flag maps port 80 of the host machine to port 80 of the container, allowing external web traffic to reach the nginx server running inside the container. Finally, the last segment, nginx, specifies the image we are using to create the container. Podman will pull this image from a repository if it is not already available locally. As a result, this command sets up a running nginx web server ready to serve content to clients. In this piece of code, we define a Kubernetes deployment for an nginx web server. The API version indicates we are using version 1 of the apps API, which is standard for managing deployments. The kind specifies that we are creating a deployment resource, which helps manage and scale instances of the Nginx container. Within the metadata section, the name of the deployment is set to Nginx test deployment, which will be used to reference this deployment. Under the spec section, we define that we want to maintain 2 replicas of the pod, meaning Kubernetes will ensure there are always 2 instances of the Nginx container running. The template section is critical as it describes the structure of the pods that will be created. Inside spec, we specify the container details. Here, we name the container Nginx test and set its image to the latest version of Nginx. The ports configuration exposes port 80, which is standard for web traffic. Importantly, we also define a security context for the container. This includes SELinux options, where we set the type to container log reader T. This configuration ensures that the container adheres to SELinux policies, permitting it to log data securely without compromising the system's overall security. When working with Nginx, developers may encounter a permission-denied error, which often relates to the system's security policies, particularly those enforced by SELinux. Understanding the SELinux context is essential for troubleshooting such issues. To investigate the SELinux context of a running process, you can use the command ps.efz grep nginx. This command serves 2 primary purposes. Firstly, it lists all the running processes on the system in a detailed format, including the SELinux context associated with each process. The EFZ options ensure that you receive an exhaustive list with context information included. Secondly, by piping the output to grep nginx, you filter the results to display only the processes related to nginx. This is particularly useful for isolating the relevant information without sifting through numerous other processes. By examining the output, developers can identify the SELinux context under which the Nginx process operates. This insight is invaluable for troubleshooting access issues, enabling modifications to the context or policies to ensure proper operation of the server. In this section, we will focus on the command used to generate a custom SELinux policy for your container application. The command you will be using is udica-j notebooktest.json custom notebook test. Here, Udica is the tool designed to facilitate the creation of security policies based on your container's configuration. By providing a JSON file that defines your container specifications, referred to as notebooktest.json, you can automate the generation of a relevant SELinux policy. The -j flag indicates that you are specifying a JSON file as input. The name notebooktest.json is the configuration file that contains information such as the services and processes running within your container, which helps Udica understand the required permissions. The final argument, custom notebook test, is the name you are assigning to the custom policy that will be created. Once you run this command, Udica analyzes the provided configuration and generates a tailored SELinux policy, which you can then load into your system using the cmodule command to enhance your application's security without needing extensive SELinux knowledge. In summary, SELinux plays a vital role in securing containerized workloads. Its ability to enforce strict security policies allows organizations to safely utilize containerization while minimizing risks associated with compromised containers. The beauty of SELinux is its versatility. It not only provides a robust security model for simple scenarios, but also scales effectively when it comes to managing large, complex systems with multiple services interacting with one another. By ensuring that containers remain isolated and only have access to the resources permitted by their policies, SELinux acts as a guardian at the gates, keeping your system secure and your applications safe. The next time you deploy a containerized application, remember, SELinux doesn't just add security, it adds peace of mind. Kubernetes is a popular container orchestration framework with a good community as well as commercial support. This means no matter your operating system, Kubernetes is here to streamline your container management, providing robust tools to automate deployment, scaling, and operations of application containers. In this video, we're diving into an exciting subtopic, advanced configuration with Kubernetes and SELinux. Now you might wonder, why is this important? Well, it's all about enhancing security and ensuring our workloads run smoothly. Let's get started. Now let's look at the figure. This diagram illustrates the integration of Accunox with Kubernetes, highlighting key components and their interactions. At the top, we see the action of installing Accunox, which is fundamental for implementing runtime security policies within your Kubernetes environment. Moving down, the figure depicts how Accunox interacts with individual pods. It sets up runtime process-level security policies that are crucial for maintaining safe operations of your applications. The arrows indicate the flow of information and alerts regarding policy violations, which are essential for real-time monitoring and response. In the center, we see a clear distinction of the two primary outputs, app telemetry and policy enforcement. App telemetry provides vital insights into the behavior of your applications, allowing administrators to track potential security issues. On the other hand, policy enforcement ensures that the rules set forth are actively applied, maintaining adherence to established security protocols. The diagram also emphasizes the linkage to KubeArmor, which is another important component in this security architecture. KubeArmor works alongside the operating system and leverages advanced features like eBPF and LSM to further enhance security. This integration signifies a comprehensive approach to safeguarding containers at both the application and system levels. Finally, the figure concludes with a focus on the host or virtual machine, reiterating that the security measures implemented by Accunox and KubeArmor extend beyond Kubernetes, encompassing the entire environment to ensure a robust defense against threats. Understanding how to configure Kubernetes with SELinux support is crucial for any DevOps engineer aiming for solid security. When you initiate the Kubernetes cluster with kubeadm, this command kickstarts a series of containerized services. However, those services run with a default SELinux context called container T, which might not allow sufficient privileges to access all necessary files and configurations. Imagine trying to cook a gourmet meal with only a butter knife at your disposal. Frustrating, right? To begin the process of installing Kubernetes on a system that enforces SELinux, we need to make a crucial adjustment to the SELinux security context. The command seminage permissive-a container T is used for this purpose. By executing this command, we essentially modify the SELinux policy to allow the container T type to operate in a permissive mode. This means that while SELinux will still be active, it will not enforce policies on this type, allowing containers to run without being blocked by potential security restrictions. This step is temporary and is meant solely to facilitate a smoother installation of Kubernetes. Once this command is executed, SELinux ignores the security constraints for containerized applications, preventing any interruptions during the setup process. After successfully running this command, you can proceed with the kubeadm init command, which initiates the Kubernetes installation. It's important to remember that although this adjustment simplifies the installation, you will need to set appropriate security contexts for the services once the installation is complete, ensuring that they have the necessary access privileges while still conforming to security best practices. In the provided code snippet, we define a Kubernetes pod specifically for the etcd service, which is critical for storing key-value data in a cluster. The API version and kind fields specify that we're creating a pod resource, while the metadata section names the pod etcd, establishing its identity within the Kubernetes environment. The spec field outlines the specifications for the pod, particularly focusing on its container configuration. Under containers, we build the container with a specific command to run, command, and designate the container's image as k8s.gcr.io/e3.43-0, which points to a pre-built etcd image from Google Container Registry. Notably, the security context is a critical aspect of ensuring that the etcd service runs with the appropriate SELinux context. By including SELinux options type SEPostgreSQL, we instruct Kubernetes to use the SEPostgreSQL domain, granting the necessary privileges for etcd to operate correctly. This step is vital to maintain the security and integrity of the service within the cluster, aligning with best practices for managing Kubernetes security contexts. After you have implemented security contexts for your services, you can confirm the changes using the command psefgrep spct. This command lists all running processes and filters the results to show those associated with the SEPostgreSQL SELinux context. By running this command, you will verify that your services are indeed operating under the expected security domain, which takes full advantage of the permissions granted by the new security contexts. However, it's crucial to remain vigilant regarding security configurations. Once you've confirmed that your services are running with the appropriate context, you'll want to ensure that they are not excessively permissive. To restore the security posture of your deployment, you can revert to a more restrictive setting for the container T type with the command seminage permissive-d container T. This command disables the permissive mode for the container T SELinux type, ensuring that any violations of the security policy will be enforced rather than ignored, thereby enhancing the overall security of your Kubernetes deployment. This two-step process ensures that your containers run securely while allowing you to monitor the effectiveness of the implemented security contexts. In this example, we are defining a Kubernetes deployment for an Nginx application while specifically configuring SELinux security contexts for the pods. The manifest begins with setting the API version and the kind of resource we are creating, which is a deployment. We assign a name to the deployment, Nginx test deployment, and specify the desired replica count, indicating we want 2 instances of this Nginx pod running. Next, within the template's metadata, we label the pods with app Nginx test, making it easier to identify and manage them later. The core of the configuration lies in the specification of the container itself. We set its name as Nginx test, use the official NX latest image, and expose port 80 for web traffic. A crucial aspect of this setup is the security context, where we define SELinux options. By setting the SELinux type to container log reader T, we're granting the Nginx containers access to log files, allowing them to read performance data without compromising security. This configuration helps ensure that only the necessary permissions are allocated, adhering to best security practices in a Kubernetes environment. However, a word of caution. Unlike Docker, Kubernetes doesn't allow for changing SELinux labels on mapped volumes, except for single-node deployments. This means the SELinux context assigned will be retained as configured. So you'll want to ensure that any volume you map into your containers is appropriately labeled with container file T to avoid any permission issues. This is like setting up a proper guest list before a party. You don't want just anyone to sneak in. Now we'll wrap up with a brief overview of some advanced SELinux Boolean configurations that can be tweaked to allow certain actions for our containers. For example, using the Boolean container manage cgroup lets containers manage cgroups, which can be critical in resource-constrained environments. Another Boolean, container connect any, allows containers operating under the container T domain to connect to any TCP port, which can be crucial for services that need to communicate dynamically with other components. Tuning these SELinux Booleans can help us achieve a balance between necessary operational flexibility and maintaining robust security controls. In summary, we've gone through a journey together. We learned how to set up our Kubernetes cluster to effectively use SELinux for enhancing security, how to define SELinux contexts for services and pods, and even how to fine-tune SELinux settings through Booleans. This combination of advanced configurations not only makes our applications more secure, but also positions them to perform optimally under tight security restrictions. So as we finish up, remember, a secure system is a happy system. And with that, let's keep our containers safe, sound, and performing at their best. Thanks for tuning in, and happy Kubernetes configuring. Until now, we have been working with an existing SELinux policy by tuning our system to deal with the proper SELinux contexts and assigning the right labels to files, directories, and even network ports. You might be wondering, what exactly is SELinux and these policies they're talking about? Great question. Let's dive in and unveil the fascinating world of SELinux policies together. SELinux, which stands for Security Enhanced Linux, is a powerful security framework that provides an additional layer of access control. It enforces access control policies that confine user programs and system services to the minimum amount of privilege they require to perform their jobs. In simpler terms, SELinux acts like a very strict supervisor, making sure that everything on your system behaves itself. It does this through policies, which define what actions users and programs can perform. So, What are SELinux policies, and why should we care about them? Policies in SELinux are like a rulebook. They dictate how processes interact with each other and with the various resources on the system, such as files and devices. Imagine you have a bank, and inside that bank there are different levels of employees, tellers, managers, and security officers. Each of these positions has different levels of access. Similarly, SELinux uses policies to specify which processes can access what files or communication ports. But it's not just about keeping things orderly, it's about security too. By restricting the interaction between processes and files, SELinux can help prevent malicious software from doing any harm. So, while the policies define the relationships, they also play a crucial role in fortifying the system against threats. And trust me, that's something you'll want to have in your corner when managing a system. To check whether your web server is allowed to send emails under the current SELinux policy, you can use the command getcbool httd can send mail. This command specifically queries the SELinux boolean named httpd can send mail, which controls the permission for the web server, often running under the HTTP daemon HTTPD, to initiate mail sending operations. When you execute this command in your terminal, it returns the current status of the boolean, indicating whether the web server is permitted to send email. If the output displays off, it means that the policy restricts the web server from sending emails, effectively disabling this capability. To enable email sending, you would simply need to flip this boolean to on. Adjusting this setting allows you to tailor your system's security to better suit your operational needs, while maintaining the protective measures SELinux provides. This process exemplifies the flexibility of SELinux in accommodating varying requirements without compromising overall system security. To change SELinux settings, you can execute the command setcbool-p httpd can send mail on. This command is specifically used to modify a Boolean setting associated with SELinux, which is a security mechanism in Linux operating systems. The setcbool utility allows you to enable or disable Boolean settings that affect how processes operate under SELinux policies. The -p flag is particularly important as it ensures that your changes persist across system reboots. This means you don't need to reapply the setting every time the system starts up. When you toggle a Boolean like httpd can send mail, you are informing SELinux to modify the behavior of the HTTP daemon regarding its ability to send emails. It's a powerful capability that enables further flexibility in web application configurations. However, caution is advised when modifying SELinux settings. Toggling Booleans without fully understanding their implications can inadvertently grant excessive permissions, potentially compromising system security. Always consult the relevant SELinux documentation to verify the specific policies being modified and to comprehend their potential impact on your system's security posture. To create a custom policy module in SELinux based on denied actions, the first step is to analyze the audit logs. The command grep httpbarg audit.log audit to allow httpd policy serves this purpose. This command fetches any entries in the audit log specifically related to the HTTPD service, which is crucial for understanding what actions were denied. The output is then processed by audit to allow, which translates the log denial information into a new policy module named HTTPD policy. This module encapsulates the permissions required for the HTTPD service to function properly without further denials. Once the policy module is generated, the next step is to load it into the SELinux system. This is accomplished using the command cmodule-die htpolicy.pp. By running this command, the newly created policy module is integrated into SELinux, allowing it to recognize and permit the actions that were previously denied. This process not only resolves access issues for the application, but also enhances the overall SELinux policy to better suit your specific needs. After executing these commands, it is advisable to verify that the changes are effective and operational as intended. The command cmodule-l is a crucial tool in managing SELinux policies on your system. When you execute this command, it provides a comprehensive list of all currently loaded SELinux policy modules. This overview is essential for administrators, as it reveals the active policies at any given moment, enabling effective monitoring and management of security configurations. By understanding which modules are loaded, you can better assess the security posture of your system and ensure that all necessary policies are in place. This ongoing oversight is vital, particularly in environments where applications and services may frequently change, necessitating updates or replacements to existing policies. Regularly reviewing these modules not only supports compliance with evolving security requirements, but also helps mitigate potential threats. If you discover a module that requires modification, or if you need to adapt to new operational needs, knowing how to list your active modules sets the foundation for effective policy management. Ultimately, maintaining this awareness contributes significantly to the overall security and efficiency of your system's operations. Now let's look at the figure. This code snippet focuses on integrating SELinux object classes into a policy graph database using a CSV file. The first line demonstrates how to load the CSV data, specifying the source file and aliasing it as vector. The match clause captures existing object classes in the database by matching on the attribute name from the loaded vector. It ensures that only relevant entries corresponding to the vector's names are processed, thus linking the new data to the existing structure. Following this, the set clause is utilized to update the access vector for the matched object classes. It combines the current access vector with the permissions listed in the CSV file. This is achieved using the apa.col.union function, which efficiently merges the existing permissions with the new ones provided in the vector, allowing the system to extend its policy capabilities seamlessly. This flow illustrates the process of enhancing security policy definitions in SELinux by leveraging data-driven approaches. Such methods not only improve system flexibility, but also reinforce security by ensuring that policies can adapt to new requirements as defined in the CSV input. In this chapter, we're diving into the exciting world of advanced policy management techniques within SELinux. If you've ever felt like SELinux policies are a labyrinthine puzzle, fear not. We're going to simplify things and make it engaging. We'll cover three main topics: working with SELinux booleans, handling policy modules, and replacing or updating existing policies. To manage SELinux booleans, we start by checking the current status of the httpd can sendmail boolean with the command getCbool httpd can sendmail. This command reveals whether the boolean is currently enabled or disabled, allowing administrators to understand if the web server has permission to send emails. If you find that the boolean is disabled and you want to enable the web server to send emails, you would use the command setCbool httpd can sendmail on. This command immediately toggles the boolean to an on state, granting the specified permission without having to modify the broader policy. However, to ensure that this change persists across system reboots, the command needs to be slightly adjusted. By using setCbool httpd can sendmail on, you not only change the boolean state, but also make it a permanent adjustment. The -p flag signifies that the change will be reflected in the policy, just like ensuring your baking recipe stays consistent every time you prepare it. This is essential for maintaining the desired functionality of services within a complex network environment. To view the list of all SELinux booleans available on your system, you can use the command seminage boolean-l. This command displays a comprehensive overview of the SELinux booleans that are currently set up, indicating which ones are enabled or disabled and their default values. By understanding these booleans, you can manage security settings more effectively and tailor the behavior of SELinux to meet your specific needs. If you're looking to narrow down this extensive list to find information related to a specific boolean, such as policy load, you can extend the previous command. By piping the output to grep, as seen in the command seminage boolean-l grep policy load, you filter the results to show only lines that mention policy load. This allows for a more streamlined search, making it easier to identify the exact settings and states related to a particular boolean. Such flexibility in managing SELinux booleans enables you to fine-tune your system's security policies efficiently. To view which policy modules are currently loaded on your system, you can run the command cmodule-l. This command lists all loaded SELinux policy modules, providing insight into the current security configuration and allowing you to assess which modules are active. If you need to add a new module, the command cmodule-i yourmodule.pp is your go-to option. By replacing yourmodule.pp with the appropriate file name, this command imports a specified binary policy module into the system, enabling you to customize SELinux behavior according to your requirements. However, it's crucial to manage module priorities appropriately. Modules can have overlapping rules, and in such cases, those with higher priorities will take precedence. To assign a higher priority to your new module, you can use the command cmodule x500-i yourmodule.sil. Here, the number following the BIS X flag indicates the priority level, ensuring that the rules from your new module are enforced over those of lower priority modules. This careful prioritization helps maintain a secure and well-functioning SELinux environment. To manage the policy modules in your system effectively, it's crucial to know how to remove or disable them when they are no longer needed. For instance, if you have a module named test that you want to unload, you can accomplish this with the command cmodule rtest. This command removes the specified module from your policy, allowing you to streamline your policy environment by eliminating unnecessary rules. However, there are instances where you may want to keep a module for potential future use without having its rules active. In such cases, you can disable the module using the command cmodule-d module name. This action preserves the module in your system storage but prevents its policies from being enforced, much like setting aside a game piece. It remains available but inactive. By utilizing these commands, you can maintain a clean and efficient policy environment, enabling you to adapt to changing needs without losing important configurations. To start adjusting existing SELinux policies in response to access denials, we can utilize a powerful tool called audit-to-allow. The first step involves examining the audit logs to identify any denied actions. The command grep denied var log audit.log audit-to-allow-m new module achieves this by filtering the log entries for those labeled as denied. The audit-to-allow utility then processes these entries to create a new SELinux policy module, which is named new module. This module will contain rules that allow the previously denied actions, effectively updating the SELinux policy to accommodate your needs. After generating the module, you need to load it into the SELinux policy framework so that the changes take effect. This is done using the command cmodule I new module.pp. By executing this command, the new policy module is inserted into the SELinux policy, granting permission for the actions that were previously denied. With these steps completed, you have successfully modified your SELinux policies to enhance system operations without compromising security. One important thing to remember, though, the modules you create should be named thoughtfully. Instead of generic names like local policy, use descriptive names that reflect their function, such as custom staff file access. This practice makes maintenance much easier for anyone looking at your policies in the future. With every policy adjustment, it's imperative to review generated policies carefully. The magic isn't just in creating rules, but ensuring they're precise and do not allow unnecessary access beyond what's required. Analyzing SELinux policies is a sophisticated yet essential task for system administrators aiming to maintain a secure environment. Although SELinux policies enforce mandatory access controls and manage application behavior, having insight into how these policies operate is invaluable for conducting assessments and root cause analyses. Today, we are delving deep into the world of SELinux policies, exploring how administrators can better understand the effects these policies will have on system behavior. Now let's look at the figure presented here. This is the SELinux policy summary, an essential visualization that provides a comprehensive overview of the current SELinux policies in place. At the top, we see key policy properties, including the status of multi-level security, MLS, which is currently enabled, and the policy version set at 32. This section underscores the importance of maintaining up-to-date security configurations for effective system protection. Moving to the policy capabilities, the displayed capabilities such as cgroup clabel and extended socket class indicate the specific functionality that SELinux can enforce. These capabilities play a crucial role in defining how resources can be accessed and managed within the system, contributing to a more secure operating environment. In the Component Count section, we find detailed metrics that give insight into the policy's complexity. There are 131 classes and a notable 4,981 types, all of which represent the various permissions and interactions that SELinux can manage. Notably, there are 336 Boolean values that allow for fine-tuning of security policies, while one sensitivity level indicates a unified approach to access control across the board. Next, we can observe the rule counts, which detail the vast number of actions that SELinux regulates. With over 61,966 allow permissions defined, it's evident that SELinux is pre-configured to permit many operations while still enforcing strict security measures through other counts, such as the never-allow rules. This extensive framework illustrates the balance between granting necessary permissions and maintaining robust security controls. Lastly, we have the labeling counts, where various ports and other elements are noted. The presence of 642 on PortCon demonstrates the extensive network management future-proofed within the policy. Each detail in this summary contributes to a clear picture of how SELinux operates to protect your system against unauthorized access, ensuring that users and processes interact in a controlled environment. Understanding how SELinux policies act is crucial for several reasons. Firstly, it allows administrators to conduct assessments effectively. They'll know which processes can access which resources without waiting for trial and error to expose a flaw. Secondly, it enhances root cause analysis capabilities. When something goes wrong, knowing how policies dictate interactions can significantly speed up troubleshooting. After all, wouldn't you rather have a map to navigate through a maze than randomly stumble about? Command cinfo policy.sepolicy-2 is a tool from the SELinux suite that allows you to gather detailed information about the specified SELinux policy file. In this case, /policy.sepolicy-2 represents the path to the policy file you want to analyze. By executing this command, you initiate a structured query to retrieve vital statistics regarding the loaded SELinux policy. When you run this command, cinfo parses the policy file and returns a wealth of details. This includes information about the number of classes, permissions, types, and rules that are defined within the policy. Understanding these components is crucial for administrators and developers tasked with managing SELinux, as it helps in assessing the security posture and functionality of the policies in place. Just as knowing the layout of a remodeled room is important before hosting a gathering, familiarizing yourself with the intricate details of an SELinux policy is essential for effective management and troubleshooting. This command serves as a preliminary step in ensuring that you grasp the relevant aspects before making any changes or implementing new policies. The command csearch -mount t unconfined t is a straight powerful tool for examining SELinux policy rules. By using this command, you are specifically querying the SELinux policy to investigate what permissions the mount t domain has when interacting with the unconfined t domain. The option A stands for all, which means the command will return comprehensive information about applicable rules rather than just a limited set. The /mount t parameter specifies the source domain you are interested in, while /t unconfined t indicates the target domain. Essentially, this command allows you to determine what actions the mount t context can perform in relation to anything labeled as unconfined t. This level of detail is akin to understanding the specific permissions granted to a user at a gathering. Defining clear boundaries helps prevent any unintended mishaps. By utilizing this command, system administrators and security professionals can ensure that applications behave as expected under SELinux policies, thereby maintaining system integrity and security. When it comes to visually analyzing policies, APOL is a game changer. This graphical tool allows administrators to load a target policy and conduct comprehensive analyses. Users can navigate through types and attributes to see how they are interrelated. Once opened, you begin with selecting the target policy, choosing a type to inspect its details. With options to visualize the relationships between different aspects of the policy, it's like giving your policy analysis a high-definition makeover. Central to SELinux policy behavior is the concept of domain transitions. These transitions describe how a process can change its executed domain based on specific actions, essentially deciding which permissions apply when a process transitions from one domain to another. For instance, when a process in the guest T domain executes a binary labeled abr helper exec T, it can change its context to abr helper T. This control prevents potential privilege escalations, ensuring that even if a process behaves unexpectedly, its capabilities remain bounded. The CSearch tool is a powerful utility used for querying SELinux, security-enhanced Linux type transitions. The command csearch ts guest t c process specifically focuses on investigating the transition of types associated with processes. The NAS-T flag is indicative of a request for type transition information. The NAS-S option is used to specify the source type, which in this case is guest T. This represents a specific domain or context within the SELinux policy, often associated with guest users or processes. By querying transitions involving this type, you can understand its interactions and permissions within the SELinux environment. Lastly, the maxc process parameter indicates that we are interested in the context of processes. This gives insights into how the guest T type governs the behavior and permissions of processes, affecting their capabilities and security restrictions. Understanding these transitions not only clarifies how policies are structured, but also highlights their critical role in maintaining system security and integrity. Now let's look at the figure displayed on the screen. This interface represents a tool used for analyzing SELinux policies, specifically within the APOL environment. On the left side, we see a list of various types associated with different processes and applications within the system. Each entry, such as Mount T and Motion T, indicates different security contexts assigned to domains and applications. This classification is crucial for managing the permissions and access controls that each type has. In the central area, there's a search criteria section where administrators can input specific type names or attributes to filter their analysis. This feature enables users to focus on particular domains or to identify attributes like whether a type is permissive. For instance, selecting the permissive checkbox filters the results to show only those types that operate under a permissive policy, highlighting potential security considerations. The results section at the bottom provides a detailed table view of the selected types, along with their associated attributes. Here, we can see entries such as Network Manager exec T, which includes specifics about the type's configuration and file characteristics. This breakdown is instrumental in assessing how these types interact with the broader policy framework, allowing for a thorough review of potential vulnerabilities stemming from data flow between different domains. As we analyze this figure, it's essential to recognize how these tools facilitate the review of data paths and help identify where sensitive information could inadvertently leak. Each type and its attributes play a vital role in maintaining a secure environment, ensuring that information flows appropriately without compromising system integrity. In the context of security policy management, the command cdiff_policy.31 sysfs SELinux policy serves a pivotal role in comparing two SELinux policy files. The first argument, policy.30, represents the modified policy that you have configured or tweaked. The second argument, /sysfs SELinux policy, points to the currently active policy on the system. By executing this command, you can efficiently identify the differences between the modified and the active policy. Understanding these differences is crucial, especially if you're uncertain whether the adjustments to your policy improve security or might inadvertently introduce vulnerabilities. cdiff provides a clear, comparative overview that highlights changes, enabling administrators to pinpoint specific alterations and their implications. Additionally, this comparison can empower you to adapt your security policies over time, ensuring they remain effective against evolving threats. If you discover that your recent changes have led to a decline in security, you can revert to a previous, more secure version, thus reinforcing the integrity of your system's security posture. In conclusion, the overview of SELinux policies is rich and complex, offering a plethora of tools and methodologies to ensure system integrity. Understanding their behavior and implications not only empowers administrators but also enhances the overall security posture of their systems. It is crucial to continually assess analyze, and adapt to the requirements prompted by the evolving landscape of security threats in the IT world. So, fellow administrators, keep your policy tools sharp. After all, a well-informed system is a secure system. Another analytical investigation that can be carried out on SELinux policies is information flow analysis. Unlike domain transitions, which look at how one domain can gain a certain set of permissions through transitions to another domain, information flow analysis looks at how a domain could leak, purposefully or not, information to another domain. Information flow analysis helps us understand the intricate web of data transfer among various domains within a system. It's essential for security because data leaks can occur unintentionally through various channels, leading to vulnerabilities. In this section, we will dive into how to conduct an effective information flow analysis and highlight its importance for maintaining security in SELinux. Now let's look at the figure, which presents a detailed interface for a type enforcement rule query in SELinux. This interface allows users to define and analyze the various security rules that govern information flow between different domains. At the top, we see options for rule types, such as allow, never allow, and audit allow, each serving a specific purpose in controlling permissions within the SELinux framework. These selections play a critical role in establishing what actions are permitted or blocked, laying the groundwork for secure data handling. In the center of the interface, we have fields for specifying the source type or attribute, which in this case is indicated as mount T. Below this, the target type is set to glustered T. This configuration demonstrates how a source domain can dictate what kind of access a target domain receives. The indirect checkbox is marked, highlighting that the analysis considers not only direct permissions, but also potential indirect paths through which data could flow. On the left side, the Object Class menu lists various socket types relevant to the operations being analyzed. This specificity is crucial because it helps identify the exact resources involved in the information flow. The permission set area further illustrates the granularity of control, detailing actions like accept and access, as well as the ability to invert or clear these permissions. Such flexibility allows administrators to tailor access control to meet security requirements accurately. Lastly, within the results section, we see concrete examples of rule enforcement. It displays entries indicating allowed interactions between different domains and their associated object classes. This section is instrumental for evaluating and troubleshooting the current policies in place, ensuring that any security gaps or unintended access paths can be promptly identified and addressed. Through this visual representation, users can navigate the complexities of SELinux information flow, strengthening their system's security posture. To perform effective information flow analysis, we can utilize various tools designed for this specific purpose. One such tool is called APOL. After loading in SELinux policy in APOL, we can select the option for information flow analysis. This interface is user-friendly and supports several options to fine-tune our analysis according to specific needs related to information flows. The tool provides insights into the paths data takes between domains, highlighting potential vulnerabilities. You might encounter toggles such as the minimum permission weight option, where actions are assigned weights to reflect their significance, from less crucial operations to critical ones. For example, the lock operation might have a weight of 1, while a write operation could hold a weight of 10. Adjusting these weights allows the tool to focus our analysis on the most pertinent flows that could lead to information leaks, and determine which actions are more plausible for data exchanges. If an action is rated with a higher weight, it poses a greater risk in terms of potential information leakage. Now let's look at the figure. This interface displays the various settings and options available for managing permissions within a specific analysis tool. At the top, we see the Workspace menu, which offers essential functions like creating a new analysis, loading previous settings, and saving the current workspace. These features allow users to maintain their progress and streamline their analysis work. Moving down the interface, we observe a detailed configuration area. Here, users can specify the source and target types, identify attributes using patterns such as indirect or regex, and effectively set the context for their analysis. The Object Class section further categorizes specific types of permissions and actions, allowing for more refined control over the data being analyzed. In the central area of the figure, the permission sets are highlighted. This is where users can select specific permissions to evaluate, including options like accept and access. The flexibility to include or exclude certain permissions, as highlighted in the original script, is crucial for focusing on potential data leakage hotspots. The bottom section presents the results of the configured permissions. This display lists the rule types, source, target, and associated permissions, providing a clear overview of the access paths defined in the analysis. Each entry indicates whether the permissions are allowed or restricted, aligning with the broader goal of understanding data flow and identifying areas of potential risk. As we analyze this figure closely, we see how the permission map can influence the directionality of data flow. Users can visualize how data is being accessed or modified, which is vital for quickly identifying significant access points that could lead to substantial data breaches. In this section, we will analyze the information flow between two security domains, specifically staff T and guest T, using the SELinux command line tool. The command employed is designed to evaluate how information can potentially traverse between these domains, which is crucial for identifying vulnerabilities that may lead to data leaks. The command starts with SELinux, which indicates the tool being used. The -s flag signals that we want to analyze the information flow, while the -m option specifies the permission map path, in this case, /var/sepolgen/perm map. This permission map is essential because it contains the configurations that define how permissions are managed between different domains. If a custom permission map hasn't been created, the system's default will be utilized. Next, the -s and -t flags represent the source and target domains, respectively. By specifying staff core T as the source and guest T as the target, we are instructing the tool to track potential information flows from staff to guest. Finally, the -w10 option filters the results by focusing on permissions with a weight of 10, ensuring that the output highlights only the most critical pathways. This thorough analysis is vital for maintaining security and mitigating risks associated with data exposure. The command cpolicy communicate-s-PostgreSQL-t-t staff T is a powerful tool in SELinux for checking information flows between different security domains. In this instance, the -s flag specifies the source domain, which is PostgreSQL-t, and the -t flag designates the target domain, staff T. By executing this command, you prompt the system to analyze how types of data can move from the PostgreSQL domain to the staff domain. Once the command runs, it produces a list of intermediate types, which are the potential pathways that allow data to be written from the source to the target domain. This process is of vital importance in SELinux policy management, as it not only reveals the direct flows between these domains, but also highlights any intermediate steps, thereby revealing potential security implications. Understanding these flows helps administrators manage risks related to data leaks, ensuring that sensitive information does not unintentionally cross boundaries it should not. Overall, this command serves as a quick and effective means to assess and visualize information flow within a SELinux environment, enhancing both security and policy comprehension. To sum up, mastering information flow analysis within SELinux represents a significant step toward securing environments, adhering to compliance requirements, and enforcing best security practices. By using the right tools and approaches, security administrators can mitigate risks, control data paths, and ensure that sensitive information remains protected from external threats or unintentional leaks. In conclusion, while navigating the complexities of SELinux and its policies may seem daunting, especially when it comes to analyzing information flow, clarifying these concepts, and using the right tools can make a world of difference. Always remember that analyzing permissions isn't just about knowing what can be accessed, but understanding how data flows and where leaks might occur. Stay tuned as we further explore SELinux security measures in our next segment. Linux administrators can use SELinux controls to prevent or confine access to applications, but this is not always the requirement at hand. Understanding SELinux domain management begins with how SELinux enforces access controls and application confinement to enhance system security. Let's dive into the paradigm of SELinux, where each application runs under a specific domain that determines what resources it can access. Think of these domains as virtual fences. They allow access within certain bounds, preventing unwanted interaction that could lead to security breaches. Therefore, understanding SELinux's management of domains is crucial for Linux administrators aiming to strike a balance between application performance and security. Now let's look at this figure. It illustrates the relationships between different SELinux types, specifically highlighting the interaction between the HTTP PHP and PostgreSQL domains. Each domain represents an application or service, which in this case includes a PHP application running on a web server and a PostgreSQL database. The arrows in the diagram indicate the permissions and interactions allowed between these domains. For instance, the HTTP PHP domain can connect to the PostgreSQL as shown by the arrow labeled Connect to. This indicates that the PHP application has the ability to initiate a connection to the PostgreSQL database, which is essential for dynamic web applications that require database access. Further examination of the diagram reveals additional arrows labeled recv and rev-from. These denote that the PostgreSQL domain is permitted to receive various types of data from the HTTP PHP domain. This bidirectional communication is crucial for operations where the web application queries the database for information, thereby ensuring data flow between the two applications while maintaining SELinux's security policies. Additionally, there is a connection to the Unix stream S type, which represents Unix socket communication. This further emphasizes how SELinux controls interactions not just at the network level, but also through local sockets, illustrating the comprehensive nature of its security model. By visualizing these relationships, administrators can better understand how to configure permissions effectively, maximizing both functionality and security. To begin creating a SELinux policy for the application myapp, the first step involves using the command sepolicy generate-n myapp init/usr-bin myapp. This command initiates the policy generation process by defining a new domain specifically for myapp. The -init flag indicates the path to the application's executable, which aids in analyzing the required permissions based on its operations. Once the policy is generated, the next command is make def/ushare SELinux devel/makefile myapp.pp. This step compiles the generated policy into a binary format, producing a policy package file named myapp.pp. By using the makefile from the development directory, it ensures that the compilation adheres to SELinux's standards and practices. Finally, to implement the compiled policy into the SELinux system, the command cmodule-imyapp.pp is executed. This command installs the newly created module into the SELinux policy framework, making the specified permissions active for myapp. With this installation, the application can now operate under a defined security context, ensuring that the necessary permissions are enforced as per the policy crafted by the administrator. The command ausearch-m-avc-ts recent is essential for administrators managing SELinux policies. It retrieves recent access vector cache (AVC) messages, which log denied actions and interactions within the SELinux environment. This command focuses specifically on the AVC messages, as they provide crucial insights into why certain actions were blocked, thus helping in troubleshooting issues related to permissions. The m-avc option indicates that we want to filter the results to show only AVC messages, which are generated when a certain action is denied based on the current SELinux policy. Understanding these messages allows administrators to pinpoint specific access violations and the reason behind them. The -ts recent option specifies the time frame for the search, ensuring that we are looking at the most up-to-date log entries. This is particularly useful for quickly identifying whether any recent changes to the SELinux policy might have led to unexpected denials, enabling prompt adjustments to the security policy as needed. Thus, this command serves as a critical tool for maintaining the balance between security and functionality within a system using SELinux. In this section, we focus on how to configure a domain for our application, myapp, to run in a permissive manner. The primary command to achieve this is seminage permissive a myapt. This command is part of the SELinux management tools and allows us to modify the security context of our application temporarily. By marking the myapt domain as permissive, we are essentially telling SELinux to relax the security policies normally enforced on the application. Instead of outright blocking any operations that violate these policies, SELinux will now log such denials while still allowing the application to execute those actions. This is particularly useful during troubleshooting or when we're uncertain about the specific permissions required by our application. However, it is crucial to exercise caution when applying this permissive setting. The flexibility it provides might inadvertently expose the system to security vulnerabilities. Therefore, it is recommended to closely monitor the logs for any denials during this testing phase and to update the security policy accordingly. Remember, this permissive state should be temporary. Once the issues are resolved, you should revert to the standard confined mode to ensure the application's security. Furthermore, when it comes to managing SELinux domains, understanding the lifecycle of application domains proves vital. Each application may require a unique domain, but an overabundance of them can complicate system management. Thus, administrators often seek to utilize categories of policies, these group applications that share similar functions, into a single domain to streamline their management without sacrificing security. Consider web applications, where the Apache web server runs many applications with similar functionality. Instead of creating individual policies, a category-wide policy allows web applications to share permissions, ensuring efficiency in handling security without micromanaging every application's needs. The rule provided in the code snippet is a specific SELinux policy statement that governs how the application myapp interacts with system resources. In this case, the rule is designed to allow myapp, classified under the type myapt, to bind to a TCP socket on the system. The action it permits is specified by nameBind, which refers to the operation of associating a socket with a port number. This rule addresses potential access issues that might arise when myapp attempts to communicate over the network, particularly on port 8080. By explicitly allowing this operation, the policy grants the application necessary permissions while upholding SELinux's overarching security framework. SELinux operates on the principle of least privilege, ensuring that applications only have access to resources they specifically need. Thus, incorporating this rule not only facilitates the required functionality of myapp, but also ensures that it operates within the security boundaries established by SELinux, mitigating the risk of unauthorized access or exploitation of system resources. Now let's look at the figure. This diagram illustrates the relationship between various components in an SELinux environment, specifically highlighting the interactions between Apache and MariaDB, along with their respective contexts. On the left side, we have Apache, represented by the label HTTPDT. This denotes the SELinux type associated with the Apache web server. Below it, we see the directory path /var/w/html, indicating where the web content is stored. This directory is assigned the context httpd/syscontent_t, which defines the type of content Apache is permitted to access for serving web pages. Moving to the right, we encounter MariaDB, identified by MySQLDT. This indicates the SELinux type for the MariaDB database server. Directly beneath, the path /datasMySQL is shown, corresponding to the location of the MariaDB database files, which are granted the context MySQLDBT. The arrows in the diagram illustrate the flow of permissions and interactions between these components. The solid lines signify allowed access, indicating that Apache can serve content from the directory under its designated context. Meanwhile, the dashed lines represent potential restrictions, suggesting that Apache and MariaDB do not directly interact. This separation ensures that each application operates within its defined security boundary, reflecting SELinux's emphasis on strict domain management. Notice the red cross in the center of the diagram. This serves as a critical reminder that there are clear segregation and access controls at play. It emphasizes the importance of defining explicit permissions while minimizing unnecessary interactions between services to maintain a secure environment. Overall, This figure encapsulates the essence of SELinux domain management, showcasing how you can effectively confine services while still allowing them to function as required. Each component adheres to its designated security context, paving the way for a robust and secure application ecosystem. The SEPolicy command in SELinux is a powerful tool designed to create initial SELinux policy modules. Imagine this as a first draft of a policy that administrators and developers can carefully refine to meet specific needs. This isn't just throwing together a few commands. It's about strategic planning and understanding your application environment. The SEPolicy generator draws upon various system resources, like the package database of your distribution, to decide which resources to incorporate into the generated SELinux policy files. When you use the SEPolicy generate command, it essentially opens a gateway to the world of application-specific SELinux policies. But from the start, it requires you to inform it about the type of application you're dealing with. There are several types supported, each requiring a different approach. Let's run through them. You can recognize user applications with the JASH application flag. These are the regular applications you might launch and interact with on a desktop. Then there are system service applications indicated by the init option, running in daemon mode or with their own user. Dbus applications, which are initiated by the Dbus messaging system, are represented with the Dbus flag. And don't forget about Common Gateway Interface (CGI) scripts, identified by the -CI option. These guys can have their own domain to keep things isolated from the web server's domain. Then there's the sandbox option for applications that need a bit more restriction than your average user application. Sandboxing is becoming more important as we look at securing environments where untrusted applications might run. Each of these options can tailor how the SELinux policy expands to include the necessary components for the application in question, leading to a robust policy that protects your system while allowing necessary functionality. So now that we have this understanding of the SEPolicy generate command and the different types of applications it supports, let's look at a practical example that showcases how powerful this tool can be. Let's generate a policy for the pgpool2 application, a load balancer for PostgreSQL databases. To kick things off, we'll use the command sepolicy-n pgpool-init/bin pgpool to create a new policy named pgpool for the /usrbin/pgpool binary. This command generates a skeleton SELinux policy based on the reference policy code style. By doing this, you establish a foundational framework for the pgpool service, which you can customize and expand as necessary. Once the skeleton policy has been created, the next step is to build and load the policy into memory. This is accomplished using the command make-f yar//selinux/devel makefile pgpool.pp. Here, we utilize the makefile provided by the SELinux development environment to compile the skeleton policy into a loadable module file, pgpool.pp. Now that we have our policy module ready, we load the new policy into the SELinux environment with the command cmodule-pgpool.pp. This command installs the pgpool policy module, effectively integrating it into SELinux, allowing the system to enforce the new rules tailored for the pgpool application. After loading the new SELinux policy, it's essential to ensure that the file system reflects these changes accurately. This is where the first command comes into play. It relabels the specified directories and files related to pgpool. The command restorecon-rvf-usrbin pgpool/log-pgpool var run pgpool recursively applies the correct SELinux security contexts to the files in these locations. This step is critical for proper operation, as it ensures that any security policies associated with the pgpool service are correctly assigned, which helps prevent permission-related issues when the service runs. Once the file system has been properly relabeled, you can proceed to start the pgpool service using the second command, systemctl start pgpool. This command initiates the pgpool process, allowing it to run and manage database connections as intended. After executing this command, your newly configured pgpool service should operate smoothly. However, while the initial setup is straightforward, continuous monitoring and adjustments may be needed to optimize the configuration based on real-world usage and requirements. The command-cat/larg/audit/audit.log audit to allow dar is a powerful tool for administrators managing SELinux policies. It begins by reading the audit log, which is located at /var-log-audit/audit.log. This log file contains records of AVC denials, detailing the events when SELinux has blocked actions or access based on the current policies. These denials may indicate issues, such as pgpool not being able to operate correctly due to restrictive SELinux settings. By piping this log through audit-to-allow-r, you convert the raw audit log data into more user-friendly information. The -r flag specifically generates a report of the required rules based on the unfettered activities that SELinux denied, which can guide you in updating your SELinux policy. The output will show what permissions need to be granted to allow pgpool or any other application to function seamlessly. This process highlights the ongoing necessity of refining your SELinux policies to maintain the delicate balance between robust security and application usability. As you adapt and enhance your systems, always remember to assess the implications of the policies you are creating or modifying. Let's discuss some limitations of these automated policy generators. First off, many of them tend to target specific application categories. So while using tools like Utica, which primarily targets containerized workloads, they might not be much help for general-purpose applications. Moreover, generated policies often only support a single policy format, either reference policy style or CIL style. So if your organization opts for a particular style, it's best to stick with that approach. This consistency helps lower the learning curve for new developers and avoids confusion about which style to use for application policy development. In conclusion, the SEPolicy command is invaluable in the SELinux toolbox. It's fast, it's effective, and it gets you started with security-focused policies. However, never forget that developing robust, fine-tuned policies requires understanding your application and monitoring its performance over time, ensuring the generated policies evolve along with your needs. Through this journey of understanding advanced policy generation techniques, we've seen the SEPolicy command empowers administrators to take control of SELinux policy generation. It's about crafting that first draft and then rolling up your sleeves to refine it, tune it, and ensure that it's not just functional but secure. Be diligent, stay informed, and keep iterating on your policies. Security is a constant journey, not a destination. The reference policy serves as the foundation for SELinux policy development. It is the most extensively utilized source, having evolved through years of dedicated effort from a vibrant development community. What you might find particularly interesting is how this evolution has led to a rich ecosystem of tools that support SELinux development, such as Audit-to-Allow and SELint. These tools are essential for creating, modifying, and validating SELinux policies, ensuring that they meet operational and security standards. In this section, we will look at how to download the reference policy for SELinux directly from its GitHub repository using a git command. The command you will use is git clone git/github.com/SELinuxproject/refpolicy.git. This command is a fundamental operation in Git that allows you to create a local copy of a remote repository. When you execute this command in your terminal, it initiates the cloning process, which brings the entire content of the reference policy repository into your local environment. What this means for you is that you now have access to all the files, structure, and documentation provided in the repository. This ability to clone the repository is crucial, as it allows you to adapt and customize the policies to suit the specific needs of your Linux distribution. With the reference policy in hand, you can start to modify the SELinux policies to better align with how your distribution is intended to function. This flexibility is instrumental in enhancing the security and operational efficiency of your system. Diving deeper, the reference policy contains a core directory with multiple subdirectories like modules and support. Each holds crucial information and definitions that will immensely aid you in developing your custom policies. The modules directory contains the real meat of the policies, while support houses reusable macros that streamline policy development. To navigate through these modules, you might find the structure self-explanatory as it categorizes policies into various types, ranging from application policies to system policies. When you're ready to develop application-level policies, start by identifying the types of applications you'll be dealing with. Are they end-user applications, administration interfaces, or system services. Each type may need a specific approach in policy development. For instance, end-user application policies typically focus on access to personal data and might call user domain interfaces, while services will often have simpler structures. Once you understand what type of application you're dealing with, it's crucial to get familiar with the supporting tools available. Audit to Allow is particularly helpful when you want to deduce the rules needed based on access vector cache (AVC) denials. It can guide you through the maze of policy definitions, helping ensure you grant the minimal necessary permissions for your applications. In this part of the tutorial, we will focus on using the SELint tool to assess the quality of your policy files. The command provided, SELint mypolicy.t, is the straightforward way to initiate this process. By executing this command in your terminal, you instruct SELint to examine the specified policy file, in this case, mypolicy.te. When you run this command, SELint performs a comprehensive analysis of the policy file. It checks for adherence to established coding conventions and style guidelines, ensuring that your code is not only functional, but also readable and maintainable. This analysis also includes error checks, which are crucial for identifying potential issues that could arise during deployment. Once the analysis is complete, SELint will present you with a report detailing any violations or areas requiring improvement. This feedback is invaluable for developers, allowing them to refine their policies before they are implemented in a production environment. By leveraging SELint, you can enhance the reliability and quality of your policy files, reducing the risk of errors at deployment. Now let's look at the figure illustrating the relationships between various user domain templates in SELinux policy development. This diagram emphasizes the modular nature of policy development through the use of interfaces, highlighting how different templates are interconnected. At the top of the figure, we see the user DOM base user template, which serves as the foundational template for defining user capabilities. It acts as a starting point for the other templates, establishing basic user permissions and functions. Directly connected to it is the user DOM login user template, which specializes the base template by adding login capabilities. This specialization emphasizes the importance of extending base functionalities to cater to specific needs within the policy structure. To the left, the user DOM restricted user template is illustrated, which adds privileged user domain capabilities. This template indicates a more constrained environment, tailored for users who require limited access without compromising essential functionalities. Connected below this is the user DOM common user template, which incorporates common privileges for end users. This template underscores the necessity for providing essential capabilities regardless of the user's status as restricted or admin. On the right side of the figure, the user DOM admin user template is displayed, adding highly privileged administration capabilities. This template's prominence highlights how administrative functionalities are distinguished from standard user permissions, allowing for a clear separation of roles within the SELinux policy framework. Overall, the figure effectively encapsulates the hierarchical and relational structure of these user domain templates, demonstrating the benefits of modular design in SELinux policy development, where interfaces serve as crucial bridges for seamless communication and functionality sharing among various modules. When structuring your policy modules, such as the myservice.t file, you'll commonly find three components: the type enforcement rules, file context definitions, and interface definitions. Each of these files plays a crucial role in the overarching SELinux ecosystem. The file context definitions, for instance, specify how particular files should be accessed and labeled, ensuring that the system enforces the rules you've defined. In this example, the code line allow httpdt sys8mmt process transition specifies a rule within the SELinux policy that governs how process transitions are handled between different security domains. Here we are focusing on two specific types, httpdt, which represents the web server domain, and sysamt, indicative of the system administrator domain. The allow directive is crucial, as it explicitly grants the httpdt domain the permission to transition to the sysamt domain. This means that when the web server needs to perform operations that require administrative privileges, it can do so without breaching the strict security boundaries enforced by SELinux. Such transitions are vital for maintaining secure interactions while ensuring that only authorized processes can elevate their privileges when necessary. By implementing role transitions in this manner, you not only reinforce security, but also maintain the integrity of your system. This approach helps in minimizing the risk of vulnerabilities that could arise from inappropriate access, ultimately enhancing the overall security posture of your applications and services. Lastly, remember to test your policies rigorously. Even minor oversights can lead to security vulnerabilities. Leverage the auditing tools provided by SELinux to ensure every rule functions as expected. With practice, developing SELinux policies will become second nature. Thank you for joining me in this exploration of SELinux policy development. Let's transform our systems into fortresses of security together. And remember, as you dive into the world of SELinux, keep your humor alive. After all, coding and security don't have to be serious all the time. Happy coding! CIL for SELinux is a powerful, lower-level syntax and language that is used to express all possible SELinux policy code. In this video, we will delve into the nitty-gritty of developing SELinux policies using CIL, or Common Intermediate Language. So grab your favorite beverage, settle in, and let's dive right into the world of security-enhanced Linux policies. At its core, CIL is designed to bridge the gap between high-level policy languages and the binary representations that the Linux kernel understands. It's a clever little language that takes complex security policies and turns them into something the kernel can digest. Think of it as the translator of security measures, like having a friend who speaks multiple languages at a party where everyone is trying to communicate but can't quite find the right words. Although it might seem daunting at first, don't let that scare you off. CIL is designed with a focus on readability, and though it's low level, that doesn't mean it's impossible to understand. In fact, once you get the hang of it, you might even find it less intimidating than trying to reason about high-level policy languages. To convert a policy package (pp) file into Common Intermediate Language, you can use the command /libxx/clhl/ppgpool.pp. In this command, the path /libx/hlfpp points to the necessary utility for the conversion process, allowing you to translate your policy file effectively. The argument pgpool.pp specifies the actual policy file you want to transform. Executing this command initiates the translation from a high-level SELinux policy format into CIL. After running the command, you will find that the new CIL output is more detailed and structured than the original .pp file. This expanded format allows for more precise modifications, enabling you to take advantage of CIL's capabilities for ensuring security within your system. By examining the output, you can gain insights into the policy's underlying mechanisms and make informed adjustments as needed. This process is essential for users who seek to refine their SELinux policies with greater granularity and clarity. In this CIL statement, we define a file context using the file_contoke structure. The first element, /var//pgpool, specifies the path and indicates that we are targeting the directory /pgpool. The use of the regular expression suggests that any files or subdirectories within this path will also fall under this context, allowing for flexible matching. Next, the term any represents the type of access that this context will apply, indicating that any subject can access this path as defined by the associated security policies. The subsequent nested structure defines the security context for objects within this file context. Within this structure, system U, object R, and pgpool var run T specify the user, role, and type respectively, which are crucial components of the SELinux policy framework. Finally, the additional S0 elements denote the security levels associated with this context, reinforcing the hierarchical nature of SELinux policies. Overall, this statement demonstrates a well-structured approach to managing security contexts effectively. In the provided code snippet, we begin by defining a new type called pgpool_port_t. This declaration is essential as it establishes a custom data type that can be utilized throughout your application or system. By creating a distinct type, you enhance clarity and organization, allowing for more intuitive handling of related data. Following the type definition, we have the line type attribute set defined port type pgpool port T. This line is particularly significant as it associates a set of attributes with the pgpool port T type. By doing so, you encapsulate specific behaviors and permissions that pertain to this type, effectively simplifying access control and reducing redundancy in your code. Instead of repeating configurations or permissions in various places, you can define them once within the attribute set and apply them uniformly wherever the pgpool port T type is utilized. This not only streamlines your code, but also enhances maintainability and scalability, allowing you to make changes in a single location that propagate throughout the entirety of your application. In this section, we delve into the implementation of constraints using CIL, Common Intermediate Language, which is crucial for managing access controls in SELinux environments. The provided code snippet demonstrates how to define a constraint that governs file read access for the staff T domain. The constrain function encapsulates the access control policy, specifying that the file read operation is subject to certain conditions. Within the OR block, there are two critical conditions combined by an AND statement. The first checks if the current domain, denoted as T1, is staff T, and simultaneously verifies that the target file type, represented by T2, is not passwd file T. This effectively enforces that if a subject belongs to the staff T domain, it cannot read the passleft file T, thereby protecting sensitive information against unauthorized access. The second condition in the OR clause ensures that if the subject is not staff T, the constraint does not apply, allowing other domains unrestricted access to the file type. This design provides a nuanced approach to access control, safeguarding sensitive files while ensuring that legitimate access is still possible for other domains. The code snippet provided defines a block named pgpool, which is specified to be of the type domain. In a structured policy approach, using blocks like this allows you to encapsulate related elements and behaviors within a defined scope, similar to how you would compartmentalize different areas in a house. By doing so, it enhances clarity and organization within your application policies. Within the context of domains, this block serves as a container that can specify various attributes and configurations relevant to the pgpool functionality. This means you can neatly define configurations, rules, and behaviors associated with that component without impacting other parts of your application. This modularity creates a more scalable and maintainable policy structure, enabling developers to later expand or modify the pgpool settings without the risk of unintended disruptions elsewhere in the code. Utilizing this structured methodology underlines the significance of namespaces in improving the readability and manageability of your code. By separating different components into distinct blocks, your application maintains a clear boundary and organization, turning complex policies into a more navigable and efficient framework. As we wrap up, remember that developing SELinux policies in CIL is akin to piecing together a complex puzzle. Each piece, whether it's attributes, constraints, or namespace organization, plays a critical role in the overall picture. There may be a steeper learning curve compared to high-level languages, but the payoff is a more powerful, flexible, and nuanced security policy. Thank you for joining this journey into the world of CIL. As you begin to synthesize this language into your SELinux toolkit, may your policies be secure and your coding adventures be ever rewarding. Happy coding, and don't forget to share your new knowledge, because shared knowledge is like adding another piece to the puzzle.